am not able to present the slides here, even though the screen is showing. Do you know why? Oh yeah, now it's so it has to be in the slide mode. It seems. Okay. I think you need both. Okay. All right, folks. Good morning, and we will wait for a few seconds, few minutes, maybe until everybody joins, because we are supposed to start at 9:30. Before we start, I just wanted to give you a general update on what I did. I kind of combined the slides of the previous day and yesterday's part of the first day lecture that I covered. Both of those day 1 and day 2 materials are posted. Probably you must have seen all of them. I also gave you access to the reports that I used to extract those graphs from. So, it is again only to go through the important points in the class, but the report is very extensive and you might benefit reading them when you have time later on. I also provided the journal articles that were used or at least gave you some idea about hydrologic extreme indices that we calculated yesterday. The paper that was discussed by Professor Venkat Reddy, as well as the other climate change paper that I was showing, Bisht et al. That talks about the Indian river basins and also the cities, the increasing decreasing trends and what kind of extreme metrics that we used. So, having gone through part of our lab yesterday, that you now have some familiarity to go for the data sources and modify the Python code that you already started with. Maybe we haven't completed, but that is a starting point. You can extend combining these papers, looking at how you want to implement for your own region. When you go back, you want to understand how climate change or the recent few years of history for your watershed, for your state, wherever you are coming from, you could do those analysis just for curiosity's sake. It might help you enhance some of these understanding, and who knows, if you think you can do it for the whole country, extending it, and you could follow the examples of that report. Center for Environmental Studies, CES, I think, is the one that I was showing. You could kind of use that 1 year analysis for the whole country, or at least pick one region where you are coming from. I think they divided them into 4 or 5 regions. You could take one region, collect all the data, start doing the sample analysis of 10 indices that we talked about yesterday. Maybe you could choose 5 that are relevant to your study area, and just kind of keep yourself warmed up with the idea of how to calculate for a given year how the extreme events have occurred in the region. That might give you little more understanding. Theory is one thing, but only when you do the analysis, when you do the calculations, you might really broaden your or deepen your understanding. Okay, I will go after the interaction, land atmospheric interaction part in the first part, and then the second part I will talk about the floods. After that we will have a break. I think we will have 2 continuous hours from me, and then Dr. Venkat Reddy will come and join for the last hour because he has some other commitments this morning. So, we will start with my lecture. Before I start, I wanted to show you, just observe this video for a second. That might be of interest to all of us. Maybe I need some help from Ishwar. I just want to project this video. It's not a PPT slide. How do we do that here? This is a video. It's not coming. Maybe it's not duplicate. Control what? Windows? So let me start from scratch here. So this is from some other source, as you see here from NASA. I don't know whether that link is still active, but the concept is still the same, that what we are going to be talking about. Just observe, this is a very quick video. Want to turn off it? Yeah. So the evaporation is happening, and then the cloud formation, both from the ocean and from the land mass, both from the land mass and also from the ocean surface. Then the clouds move to the land area. So when sufficiently you know, cool enough for them to condense, it drops the precipitation, liquid rainfall over the land, snow on the mountain tops because of the elevation difference, and then of course once it reaches the ground, it starts flowing both on the surface as surface runoff, right, and then part of it is infiltrating into this soil column and reaches the deeper aquifer and flows laterally beneath the surface. So it ends up, depending on the gradient, both of the surface and subsurface will end up in the ocean. In some cases, it might end up stored in the groundwater as a storage system. So the idea here is to show you that this is the cycle, the water cycle or hydrologic cycle that we talked about yesterday and day before yesterday, right? So maybe a picture like this helps us understand comprehensively about how these different components are partitioned for a given watershed or a given country or even a region, right? So what is the takeaway from here? The takeaway is the sun's heating on a day-to-day basis creates this dynamics. The energy balance, the water balance, and the topography combined really contributes to all these budgets, water budget, energy budget components. And this is kind of very important for us to understand, in the context of both natural system and also for the developed system, because the partitioning is different for different places depending on the development. I will stop this video here. I think most of it is covered. The purpose that I am showing is to say that the water cycle, that what we see as a pictorial representation, is shown as a movie. That's pretty basic. Most of you have understood, or most of you are familiar with those kinds of partitioning from your previous classes, and for some, if it's new, you might really kind of get a broader understanding of what's happening with respect to water cycle. So the important paper that I am citing here is this. They talk about human domination of the global water cycle absent from depictions and perceptions. When time permits, just read them through. But the highlight of that paper tells about this partitioning or water budget components for a natural system now that is modified by humans on a global scale. So when they are talking about how much rainfall on a global scale or a continental scale they get, and how that is divided from a natural system versus how now it is divided, is not represented in the left side water cycle graph or the movie that you saw. That is the idea that I am trying to drive here, that we as humans are modifying the system, but in reality we have not really captured all these water budget components for the modified watershed systems around the world. And in India or any other country where the development is happening very quickly, the changes need to be represented. For that you need data, you need models, and then a comprehensive understanding of how humans are influencing these budgets. So the numbers, don't worry about the numbers, you can read closely when you get these slides, but what I am trying to say is the numbers are different. If you look at runoff in a natural system versus the runoff that's happening with the built up area, it's different. The hydrograph peaking happens very quickly in a developed watershed compared to a natural watershed, because in the natural watershed you have time for water to percolate, infiltrate, and then part of it is going as surface runoff. In the developed watershed, like a city like Warangal, Hyderabad, Delhi, Mumbai, you have less chances for water to percolate inside, so it starts flowing right away. So that leads to high peak flows, and it ends up as floods in some cases. We will connect this part in the flood discussions later on. So this is again talking about different components dividing over a large area. I think it's on a global scale. Major fluxes and hydrologic cycle. You can see atmosphere holds relatively small amount of water compared to the ocean, right? It's really small. But then when it falls on the ground, significant portion goes 70,000 cubic kilometer per year of ET that's going from the land to the atmosphere, which becomes again part of your precipitation clouds, comes back as rainfall. So this kinds of partitioning, whether or not true for a given country, given watershed, given location, is the one that everybody wants to answer, and that's a pretty big wide open topic for some people to really ask that question. So again, this is from the textbook. People simplified in the past to calculate runoff. They know how much is the precipitation, that is the input, and how much is the loss as evaporation on a global scale or a continental scale, and come up with these numbers. As you can see here, roughly you should know, as hydrologists, as earth scientists or natural resource people, we want to know this. Geoinformatics, all of these disciplines look at this precipitation of the total amount is roughly going about 30% or so, or maybe 25 depending on the location. So as runoff, and the remaining goes as evaporation. That is how they partitioned. As the science advanced, they realized that this equation is not correct. They wanted to consider soil moisture, they wanted to consider deep drainage. Those are the two major ones in this equation that's missing. But on a global scale, to calculate the fluxes, whatever you get should be going back, right? That is a supply and demand kind of a thing, but you don't see them here. For example, for the land mass, you have precipitation divided equally, or at least more on ET side or evaporation and less on runoff. Look at the oceans. For example, here you have precipitation of 114%, but evaporation of 126%. So you got even P and E is not equal. It is little bit higher ratio, higher than 100%. How is that possible? It's possible because precipitation accumulated over oceans or adding more evaporation or contributing directly to precipitation, I mean less than your precipitation. So these ratios are constantly improved. Of course, you can see all the way from 70 to 75, 76, 78 people have studied. Again, the land mass, precipitation, evaporation, with increased amount of data, people are able to come up with better numbers, and then they also divided the same thing into continents by dividing precipitation and runoff. Runoff is in the bracket, and precipitation, mean precipitation that you see is the main number here. For example, let's look at Asia. That's one of the bigger ones, right? Out of all these things, percent of land area, 29% land area. From the references here, you can see precipitation for Asia is about global average, 0.7. and then of which 0.3 goes as runoff, the remaining goes as evaporation or evapotranspiration. So, by continent people have done this. These are kind of on a global scale. When you take multiple year data and come up with a division of these water budget components, you might more or less make it, but it changes if you are looking for a specific season or a specific location, smaller area. These influxes and outflux are different given the time. Same way, there are, I did not talk about the heat budget extensively, but what we are talking about is 4 components of energy budget. One is net radiation here, this is latent heat flux, sensible heat flux, and the other one that's missing is ground heat flux. So, net radiation coming from the sun is divided into, can I write that on the board? Can I use the board? Do we have pen here? Okay. Yeah. So, we are talking about net radiation is divided into latent heat flux, sensible heat flux, and ground heat flux, right. These are the 3 major components. We will talk more about this with all the other topics here, just to give you an idea. And of course, this net radiation is coming from the sun, right, which has got again 4 components here, short wave, long wave, right. We have short wave incoming, short wave outgoing, long wave incoming, long wave outgoing, right. There are 4 components here. They add incoming, subtract the outgoing, they get this Rn, and then they calculate latent heat flux, sensible heat flux. For a long term average ground heat flux, the amount of energy that's used for heating the ground surface is nearly 0. So, people don't consider them. So, whenever we are talking about energy budget, that is why we are seeing only latent heat flux, sensible heat flux, not the other one, the ground heat flux. I don't know, I am sorry, maybe it's too small for the last row people to see. Readable? Okay. Again, you see those terminologies here. What I am trying to say though is sun is the most active source of energy for doing all this work on a day to day basis. And of course, when you are looking at the large time scale, longer time scales, they are able to partition how much is used for latent heat flux. Latent heat flux is another interesting terminology. I think some of you might be knowing this, which is nothing but evapotranspiration. The amount of energy used to heat the water, right, that is the latent heat, and people kind of, you can easily relate. And what is sensible heat flux? Sensible heat flux is the heat that is used to heat the air. When you go outside and you sense that, oh wow, it's too hot today, that's the air that's getting heated up based on the solar energy, right. So, when on a hot day, more energy is spent on heating the air, and of course, vegetation is also taking that energy, but if they do not have moisture to supply to evapotranspire, that energy is used to heat the air. So, you can see on a clear summer day on a barren land, all the energy is directly spent on heating the air mass. So, you really feel dry, right. But in a place like this with forested area, wooded areas, trees, partitioning is happening reasonably between vegetation and the soil or atmosphere. So, that is the reason why you will see numbers that are equally divided in some cases. 65 units, watts per meter square is the common unit they normally use for energy. Roughly 30 is used for ET and heating the air, sensible heat flux. Thank you. On the ocean side, you don't heat the air too much. So that's one difference that you want to understand. I think we need to connect this also. Thank you. Oh, okay. Yeah. Thank you. Yeah, it's working. So it's very important for you to understand one big difference between land and ocean, right? You see here it's roughly divided, right, between latent and sensible heat flux, but in the ocean there is no resistance for evaporation. There is no soil that's holding that moisture or no vegetation that's holding that moisture. All the water that's available is evaporating, right? So, and of course less is spent on heating the air. So you see cooler surface, right, over the ocean, and of course that excess energy that is spent on heating the ocean water is evapotranspired, and that is the source for us to bring that moisture back to the land. So ocean land circulation, just roughly talking about, is are the ingredient for hydrology, right? So we want this kind of partitioning between land and ocean, and also moving. So now that moisture that's coming from the ocean, the graphics or the video that I showed, you understand how that cloud that is forming over the ocean, moving over the land, dumping that rain, is because of that particular term, latent heat flux, right? On a global scale, still latent heat flux is a higher component. Latent heat flux in the energy term, evapotranspiration in the water budget. When you mention in watts per meter squared, that's the energy term in the energy budget equation. That's what I showed you. But in the water budget terminology, evapotranspiration is expressed as depth units, millimeters, inches, or meters, or whatever that number. So the only difference is energy in terms of watts per meter squared versus depth units. Now, of course, this is again the same water cycle division that we are talking about. It's lifetime's work for somebody to really come up with better understanding of these budget components for the given watershed. If you are able to measure and understand how precipitation is divided into these components, that's the most authentic approach, because you have the data. You can say that this is the amount of rainfall I got, this is the amount of runoff that I am getting at the outlet of the watershed, which is the primary unit. We will talk more about that in the next few minutes. But if you don't have the data, people end up doing the modeling. If you end up doing the modeling, there are uncertainties associated with all the inputs, all the equations, and how do you validate those outputs. Those kinds of things will come into play. But you have to have a combination of good observation data set, a good model. You can merge them together to answer the question on what is a water balance for a given watershed. I asked you yesterday about what's your watershed, for each of you. If you know that watershed, go back to your place when you are done with this class, and then start thinking about this as, how can I understand for a given watershed? Am I really having data to do this simple analysis? Can I do that? Those kinds of questions you can ask. Again, in ratios they mention this, so I will not go in depth. But now another important topic I wanted to talk about, it's little not directly relevant, but it's relevant to understanding hydrologic extremes. So stable and unstable atmosphere. We are kind of, this is a hydrometeorology topic. I understand many of you will end up being a hydrologist or water resources engineers and geographers and natural resource modelers. But a general understanding of this topic will help. I'll talk about the simple equation, right? This is the lapse rate equation. The temperature, what we are seeing here, dT over dz is equal to negative g acceleration over specific heat capacity, right. So, as the temperature, as the elevation changes, as you go up from the land surface to a higher level in the atmosphere, you see drop in temperature, right. It gets cooler. This equation represents that. Can anybody tell me what is the drop in temperature that we see in certain, intervals? 6.7, I see some numbers and you are saying 1 degree, what? Unit? What is a unit? No, per kilometer, okay, but what is the unit? Temperature in Celsius, Kelvin, Fahrenheit? Celsius? Okay, you are almost correct. It's about 9 point something Kelvin, but 9.8 Kelvin per kilometer, right, and gravitational acceleration of 9.81, specific heat capacity of 1004 joules per kg. So, if you convert that equation, you get 9.8 Kelvin per kilometer drop in temperature as you go up, right. This is an important concept you need to keep in mind now. As you go up, why we are seeing cooler conditions? It's because this lapse rate is working, which makes the condition to cool in the upper layers. Now, this is another interesting thing I want you to pay attention to. Assume a balloon or air parcel, a pocket of air that is actually sitting on the ground, that's moving, and the dashed line, of course, elevation, right. I mean, this is the air parcel that's going, and then of course this is a dry adiabatic lapse rate, the continuous solid line. When it goes up, it drops. The balloon or air parcel loses the heat, or it becomes cooler, right, because of this dry adiabatic lapse rate that I am talking about. So, what happens is the drop in temperature is still higher, I mean lower than your actual lapse rate. So, that is why your air parcel is warmer and it is surrounded by cooler conditions. So, that makes it unstable in the atmosphere. The opposite is true for the stable atmosphere. When the air parcel is going, it cools faster and it is a cooler air mass than its surroundings. So, it does not destabilize the atmosphere. So, the lapse rate, if you look at 9.8 degrees, so let us say this is about 50 kilometer or maybe 25 kilometer in the atmosphere. That same balloon, when you leave, people measure all the atmospheric variables by sending the balloons every day in the morning one time, another time in the evening. All around the world they do this to collect what is happening with respect to temperature, wind speed, humidity, all of those variables they measure, bring them over to the model. All the climate models that we talked about, they use, you remember yesterday we talked about horizontal scale, vertical scale, right. For vertical scale up to whatever height that they want to model, up to maybe 1000 or from 1000 hectopascals to 0 hectopascal, about 10-12 kilometer they model. For every 1 kilometer, if they want to understand what is happening with respect to temperature, wind speed, humidity, they send these balloons out. What happens for that balloon when they fill the gas and send it up with all the sensors? When it goes up, what happens? The same balloon, does it remain the same? What happens to the size of it? Expands. It gets bigger and bigger and bigger, right, because of the condition that what we are talking about. The air expands, right, and of course it loses, of course, its um, shape and size, and of course it explodes at one point because of the of course you have pressure. So of course another important thing that I did not mention is the pressure, right? So as you go up, of course, what happens to the pressure? Decreases, so the balloon expands. So that's one of the reasons why you are talking about the connection between I mean, whenever you talk about the variables in the atmospheric column, they talk in terms of pressure units also. So again, the purpose of this, the whole thing, is to show you that unstable atmosphere is possible if the daytime heating happens, like sun comes in the morning, heats, that air mass goes up, it goes up and goes up, right? That it gets bigger and bigger, and if that air mass does not cool, and if it has the warmer conditions than its surroundings, that based on that adiabatic lapse rate that I am talking about, the condition is chaotic for the atmosphere, that creates the turbulence and creates the mixing, higher mixing, and it brings the thunderstorms and heavy rainfall events. The other thing is, of course, if the air parcel is going up and up, and if it's still cool enough, it does not destabilize, and condition is either neutral or cooler conditions. It does not really create unstable conditions. What I am talking about is the same thing in this text that you can read later when you have the slides. But I want to talk about the fundamentals of land atmospheric interaction, and I will give you a small exercise. Collectively, we will discuss one graphic that I am very much interested in showing when it comes to land atmospheric interaction towards the end of this topic. Bare soil, you have, like I mentioned before, you have more sensible heat flux, less latent heat flux. The Bowen ratio is going to be higher, which is the ratio of sensible over latent heat flux. I don't know if you have heard of the term called Bowen ratio, which is normally used. Bowen ratio, BR, is the ratio of sensible heat flux divided by latent heat flux. They calculate that. And then for vegetated or irrigated soil, BR is very less. Yeah, so I have that ratio on the right side here, on the right side of that slide here, so that you can refer. So now this is basic, these are basic elements that you want to understand. People measure conditions for atmosphere, right? I think this graphics is not completely clear, but I have provided the text material for you to download, which is available in the day 2 directory, that you can download and get the clarity of these pictures. I mean, clear illustration of these pictures. What you are seeing is the height in the atmosphere, 0, 1000, 2000, 3000, right? Potential, I mean, over time, over a daily time step, what you are seeing here on the x-axis. On the x-axis here is the time, y-axis is the height. This is how atmospheric scientists measure potential temperature, in this case, K, Kelvin, between different times, 3 a.m. and 3 p.m. You can see the sun is playing a big role. You can see the these are contours. I don't need to explain to you about contours, right? So you are all familiar. The temperature, of course, is hotter near the surface. It gets cooler and cooler when it goes up, right? And you see the pattern here, it changes. You know, this kind of a, you know, trend line that, or connection, contour lines that what we are seeing here is changing, you know, of course, between the 3 a.m. to another time period that I am going to show here for 3 p.m. So for dry soil versus moisture soil, wet soil or vegetated soil, the condition of this heating changes, right, over time. At 12 o'clock, of course, you still see a stable atmosphere, a kind of contour lines are not disturbed. In the bare soil conditions, all the energy that is spent here is used up, and of course, pretty much uniform atmosphere that you are seeing here. In the vegetated condition, of course, it takes time for that to reach, same as here, but of course, you know, you become identical here over time. Humidity, this is humidity, this is temperature. They plot this for different locations and understand how the dynamics of temperature, humidity, wind speed are all changing. Now, bring all the connections that I am talking about. We talked about lapse rates, we talked about stable, unstable atmosphere and the daytime heating. So what happens here, there is a vegetated area here, there is a dry line here, this is barren soil, right? So the cloud that is formed because of evapotranspiration over the vegetated surface goes up, right, and it forms as cumulonimbus or cumulus clouds. There are different types of clouds, we will not talk about that, but what we are seeing here is because of daytime heating you are seeing these cloud formation, right? And of course when it comes to different type of vegetation, the same cloud formation is slightly different what you are seeing here. And which one has got more potential for rainfall? This cumulonimbus clouds, these are dark clouds with heavily loaded moisture that can dump as they move. What you saw from before in that illustration or the video is that this kind of cloud formation over the ocean, over the land mass, when it happens, they just keep moving on because of the circulation that we talked about, yesterday, mass, energy and momentum. Now you got the mass and energy from these clouds, that is water and energy. When it comes through the motion or the momentum, it brings down the precipitation down. So this heavy rainfall is different for different locations. Why is that? Because the land surface conditions are changing. Look at this particular graph. I mean, we will come, maybe we will start with the items here first, our bullets. Irrigation effect has been shown to decrease air temperature. We all understand that, right? When you apply water, air temperature is little bit lesser, right? If you walk over the paddy fields, or I have driven through a highway, on both sides there are high tall corn crops, sorghum crops or corn, irrigated ones, and it creates an oasis effect, the cool effect that you can even see when you are driving through, or the trees that you are seeing on the highways, basically they cool the surface down, right? So it decreases the air temperature and it increases the relative humidity. When you are putting water on the ground, it actually evaporates, you feel sticky, you get more humid air in the surroundings, right? And then the last thing is sensible heat flux is less, and most of it is converted to latent heat flux. And this part I will talk later, decrease in the height of the planetary boundary layer. Just hold your thoughts on that first for now. Now come to this part, dry soil, sun's energy is coming down, it heats. Of course, part of it is long wave and then part of it is used for evapotranspiration. This is the sensible heat flux. Most of the energy that I was talking about is spent in heating up the air near the surface. That's why you feel hot under drier conditions. But modestly wet condition here, the same partition, again we are talking about, you remember this equation that I am talking about, latent heat, sensible heat flux. This is latent heat, this is sensible heat flux. And in a wet soil you are getting little bit more latent heat flux because that energy is used for heating the water, both from the plants and also if the soil is wet, it's going to actually use that energy. So you have more evaporation coming from this moderately wet soil. In a wet soil, of course, you see the difference between dry and wet soil. You have less energy spent on heating the air, more energy is used for latent heat flux, okay? And that is the reason for increased evapotranspiration. If you apply more water to your crop on the ground, if you apply more water to even the vegetation in the urban areas, they are going to take that energy, do evapotranspiration, keep the surface, keep the area cooler, right? This is part of heat island, urban heat discussions that are related to, but you want to understand one thing. I did not mention the PBL or planetary boundary layer property. What is that? Does anybody have a clue? So we are talking about the surface and atmosphere, right? Two systems that we are seeing in hydrometeorology, hydroclimatology. Whenever we are talking about boundary layer, anywhere above 150, 200 meters above the ground, all the way up to 10 kilometers, it's a planetary boundary layer, atmospheric boundary layer. That is the area, of which typically these clouds, what we are seeing today is a shallow cloud, right? It's a shallow cloud that I am seeing here, roughly about 2 or 3 kilometers from the land surface to the atmosphere. If it's a clear day, what happens to these clouds? They are gone. You see blue skies, right? You see blue sky. This is monsoonal clouds probably, but what I am saying is, on a clear sunny day, you probably have tall clouds up to 10, 20 kilometers, and even blue skies that you see clearly. All of these are considered as planetary boundary layer, PBL or ABL, either way they call it. Now what we did was, we tried to understand by looking not just the surface fluxes, these are surface fluxes, right? Latent heat flux, sensible heat flux, but how that is changing in the atmosphere. We have kind of modeled it. We looked at the planetary boundary layer up to 5 kilometers for an irrigated area, for sorry, this is no irrigation and this is an irrigated area. What you are seeing here, right, the clouds are taller, there is not much formation of clouds, but here the clouds are smaller. The planetary boundary layer thickness is really small here. Typically, like today, you know, what we are seeing is, there is moisture probably coming in from the ocean or monsoon clouds here, but irrigation also builds up this evapotranspired humidity or clouds that is shallower. So the difference between no irrigation to wet area, you saw the cloud, cumulonimbus cloud that I talked about, is possible for irrigated area than over the other area. The atmosphere is pretty thick or, you know, wide for the PBL without irrigation. With irrigation it is shallower, and that probably condense, if you have other ingredients in the right level, it comes down as rainfall. It for making the clouds in the irrigated area to fall as rainfall, you need other ingredients. What are those ingredients? You are talking about cooling of air mass, right? There should be a clash between warm air and cold air, then it starts downpouring. All of those things, and then of course orographic effects. There are 3 different types of rainfall. Probably you must have seen from basics. I am not touching on those things. So different types of rainfall can happen, but cloud formation is very important. If the models don't predict this PBL thickness correctly, precipitation forecast from these models can be wrong. Okay, so that's one other important element. So with and without irrigation, we looked at the thickness of the atmosphere. We found out that, of course, the thickness of convective layer is different for different regimes. Quickly talking about heat budget, again from the textbook only. For bare soil, we already touched on this many times. So what I am trying to say is, for bare soil, the solar radiation that we are having is divided into multiple things. You have more sensible heat flux again, and of course you are probably using part of it for latent heat flux, but most of it is going as heating the air column. In the vegetated area, the opposite is true, right? Basically, we are talking about the same amount of energy used by the vegetation. Turbulent sensible heat flux is there, but you have more latent heat flux. More, you can see that, you know, just symbolic representation. Less sensible heat flux, more latent heat flux. I am repeating what I said before. You saw from the graphics. This is the right kind of physical understanding that we need to have when we are talking about land atmospheric interaction. Okay, water budget. People talk about, I mentioned in energy units or water in depth units, the same thing here, right? The amount of precipitation that's used as evaporation in millimeters or meters, depth units, part of it is going as infiltration, part of it is runoff. In vegetated areas, of course, you have some amount of evaporation, but more transpiration. There are 2 components there, right? When we talk about ET, E is evaporation from the soil, T transpiration from the vegetation. Combined they call it evapotranspiration. For vegetated surface you have more ET, less runoff. Here you have more runoff. These are the basic stuff we need to understand when we are thinking about floods. That's the connection that I wanted to establish. But I am going to actually tease your brain right now by asking some questions, and interactively we will learn what's happening, because the feedbacks that we need to understand here. Let's look at one by one first. Maybe I'll take the first one on the other side. See, notations, of course, in the textbook scanned copy that I have given you, you can read them through, but I will explain here. This is precipitation, okay, this is vegetation, this is the energy absorbed on the surface, this is evapotranspiration or evaporation. So now let's talk about the evaporation, vegetation here in the center. Okay, when you have precipitation, good precipitation, what happens to the vegetation on the ground? What happens to the vegetation? They grow well, greener. It's not a desert, right? It becomes really lush green. More vegetation, more biomass. So this arrow mark tells what? This is the positive feedback. What it means is, when you have more precipitation, you have more vegetation. Direct connection, right? More precipitation, more vegetation. When you have more vegetation on the ground, what happens to evaporation? That is also high. So there is a positive feedback here. So when you have more precipitation, more vegetation leads to more evaporation. More evaporation leads to more cloud formation. More clouds can condense into precipitation. It's a nice positive feedback cycle that what we are seeing here. Of course, part of this vegetation, of course, is also helping to absorb energy. That's a positive feedback. And of course, absorbed energy is also used for increased evaporation on the surface. So it's a positive feedback in the hydrological setup that I'm talking about. In the energy framework also, the radiant energy that we are talking about will help in the atmospheric systems, that what we talked about in the the stable, unstable atmosphere. With vegetation increase, we are talking about more energy that's being absorbed here. That energy is actually again contributing towards the shallow clouds that we talked about before, which also creates conditions for heavy precipitation. So it's a nice radiative feedback, hydrological feedback that we are talking about. Okay, and I'm going to build up this further into a complicated one. This region is not our region, but it's going to help you understand a complex process. So whenever we are talking about modeling, integrated modeling of land and atmosphere, you can see how complex it can become, the process. I will break it down into one loop first, and then maybe the other loops you can figure out on your own later on. Let's start with one thing here, which is, let's say you got plenty of, I started here with the energy, right? So let me start with net radiation here. Let's say you got plenty of energy, okay, this is for the high latitude regions. High latitude means it's probably anywhere above 45 north latitude. Especially consider places like European countries, North America, or Russia or whatever, those regions, when they have the spring season, when the snow melts, ideally the clear skies form and then more radiation comes on the ground. So that's the setting I will explain. Okay, that is the kind of setting that you need to remember. When you have more energy, what happens to, connect with previous slides that we talked about, what happens to latent heat flux? You have more latent heat flux. The darker lines mean positive feedback in this graphic. Okay, darker line means positive feedback. So more energy is spent on latent heat flux. What happens when there is more energy used for latent heat flux? More atmospheric moisture, you see, right? That is another positive feedback. When you have more atmospheric moisture, there is another positive feedback here for more clouds, right? When you have more clouds, of course, then you talk about, this is on the energy side of things, right? That cloud can block the energy that's coming from the sun, right? So both downwelling short wave and long wave gets reduced because of the block of the clouds. So you got the negative feedback there. So more energy leaving the surface, more moisture, more clouds, then the energy that's getting blocked from the sun. That is a negative part of the cycle here. And then of course, with increased energy, part of the energy is of course used for sensible heat flux. That sensible heat flux increases the air temperature increases long wave. This is the passive energy that I am talking about, long waves emissivity based temperature release that we are seeing, okay. So that is a long wave radiation losses that we have. So this is one cycle that I just completed. So let us look at the other part here. When you have more ET or latent heat flux, what happens to the soil moisture? It gets decreased. More ET, more evaporation means the soil moisture goes down. That is the negative feedback that we have there. And more ET or more soil depletion of soil moisture means you have decreased albedo. What is albedo? Reflection of the energy. On a snow surface, you have 100% reflection, right? It's white surface, it just reflects. When you have darker surface, all the black body, it's a black body absorption, right? It's radiation that's getting absorbed. In a wet soil, it's kind of in the middle, but still, if the soil is sufficiently bare with no vegetation at that point, with spring season in high latitudes, your soil moisture and albedo can have negative feedbacks, meaning all the energy is not reflected back. When you have half energy that is used for latent heat flux, but half energy is still available in the column, that is going to help the soil to absorb the energy. So there is a decreased albedo, not at the 100% level, but there is a decreased albedo on a wet surface. So again, that creates another kinds of loop here. So I will not get into the details, but you got an idea now what I am talking about. This is the feedback loop that we are kind of seeing on a day-to-day basis, depending on the region where you are. It could be different in central India, it could be different in southern India or northern India, eastern India, which is different because of the topography, because of the vegetation, because of the energy that we get from the sun. Then think about the global scale. You are talking about north versus south, northern hemisphere versus southern hemisphere, right? Right now, this is warmer time periods in northern hemisphere. In southern hemisphere, it's cooler conditions, right? So you have those kinds of partitioning of energy even on a global scale becoming very complex. So we will talk a little bit about the global scale circulation and climate variability towards the end of this lecture. If not, certainly if time permits, tomorrow we will talk. But again, in discussion, before I go for that, I have to show you this. It's a very short video, just pay attention to this, okay, one sec. Just read the question that's showing up in the bottom. Will clouds accelerate warming or help slow rising temperature? Again, will clouds accelerate warming or help slow rising temperature? So we want to answer that question, right? So let's watch this video and see what they say. So slowly, let's see, the temperature is increasing. That means you're talking about more water evaporates again, right? more clouds are forming here, that is shallow clouds, 2-kilometer clouds. There are also clouds at the higher level, 20-kilometer height, right? Two different types of clouds. Low clouds, they reflect energy back. So what happens to the surface at that point? Low clouds, when the energy goes backward, today typical surface is cool. Good point. What's happening there for the low clouds? They reflect the energy back, like today outside that you see shallow clouds, you are seeing relatively cooler conditions, right? So that is a negative feedback. When the temperature is increasing, why do I call negative feedback? Can somebody explain that? Why do we call this negative? From that side, I want some answers. From our TKM friends, I am pointing you guys. Sorry, I cannot hear. Can you all hear her? I cannot, sorry. Right. So why do I call negative? Yeah, but I mean, give me a full picture. Why do I call negative feedback for this? Now I open up the floor for others. Anybody wants to jump in? Okay, but to begin with, what did I say first? What's happening for evaporation? It becomes increasing, right? It's more. Why it's more? Where did we start? Temperature was high. When the temperature is high, more evaporation, right? When more evaporation happens, more shallow clouds formation. That actually brings down the temperature now near the surface. So the temperature increases, causes temperature decrease. I think you said in bits and pieces, but I am trying to collectively say here together. Do you see what I am saying? Do you follow what I am saying? If not, just stop me here and ask the question, because this is an important point that you need to understand. When I am talking about negative feedback, we start with temperature increase, global warming, what not, it's happening and temperature is increasing and more evaporation is happening, that means more cloud. But that is not really keeping the temperature increase. Instead, it brings down the temperature now because of the shallow clouds, because of the reflective of this radiation. Right, it's a time variant factor. Basically, it can be gone by tomorrow if the shallow clouds are gone. It's, I mean, day to day process. I am talking about this as a day to day process. All the energy budget, discussions, what we are talking about is from sunrise to sunset, 6 a.m. to 6 p.m. Sun is the source, sun is the main actor here, right? If he is gone, if sun is gone, this does not work. What we are talking about, this is based on the energy that we get from the sun. Now let's finish the remaining part. Now we go to higher clouds. Increases temperature by reflecting the heat surface, right? So what happens here for higher clouds? For higher clouds, again, what happens? I call it positive feedback. What does it mean? Why?
Because short-wave radiation are getting stopped over there, but long-wave radiation are going to be stayed in the medium.
Okay, partly true what both of you have said, but what I am saying here is the cloud is not reflecting at all, because the cloud is at a higher level. I am talking about 20-kilometer higher clouds that does not even block the radiation that's coming from the sun, right? So that's basically heating up the surface and it increases more, the temperature is increasing more, So higher clouds means you will have a hotter day. In May or June, for example, before this monsoon, you hit probably 100 degrees, or let's say in Celsius 45 C, right, or more. It's because there is no way of blocking that radiation. It's coming and it's increasing. That increased temperature is probably spent more on heating the air than heating the vegetation. So that's where the feeling of sensible heat flux higher happens. It's a positive feedback. So, it's a very simple illustration of showing how clouds play a big role in changing the energy patterns coming from the sun, and how in one place it can be a positive feedback, in another place it can be a negative feedback. You know, in higher mountains where you have clouds most of the time, the energy that is spent is actually not much, right. So, it gets reflected back. So, surface is cool. Ooty or Kodaikanal in the south, Darjeeling in the north, in higher stations you can see they are cooler because of course less energy coming to them, blocked by the clouds, higher clouds, I mean mountain clouds they have, not the 20 kilometers stratus clouds I am talking about. But anyway, I wanted to kind of stop here because I think we are done with this. I will stop and go back to my slides and conclude the conversation. We will come back after the break, but what we talked about is the land atmospheric interaction. And yesterday and day before yesterday, when I talked about climate of the first kind, climate of the second kind, where does this one fall under all this discussion right now? Is that climate of the first kind? If you recall, when I said climate of the first kind, people primarily thought it's only atmosphere that controls the climate, kind of a thing, right? Compared to climate of the second kind, which is both land and atmosphere play a role in a climate condition. That's what I talked about on day 1 and day 2. So, this kind of concludes that discussion. In the land atmospheric interaction, day to day heating that happens, daytime heating that happens, sunrise to sunset, this atmosphere is very active because of the land surface. And this land and atmospheric interaction, they are very tightly talking to each other on a day to day basis, So, at least if you leave this class with this thought, oh wow, now I am seeing the clouds, now I am seeing vegetation, what is happening? So, keep thinking like that. So, it helps you broaden your understanding. So, it is not, you cannot see things in isolation, it is all connected. So, you want to understand before we get into these extremes. When we talk about extremes now, stable atmosphere, unstable atmosphere, what is happening to them, how heavy rainfall comes. Yesterday you talked about extreme event indices calculations. Now you should have all this physical context to what we are talking about, to your discussions. Urban heat island, for example, you can bring this discussion into context. Is it a problem for a given location? Is there a accumulation of moisture that you have in the atmosphere is sufficient enough to bring heavy rainfall? Will we have just isolated that from any other influences, marine influence, because ocean brings moisture, right? Whether that happens, or monsoon, Arabian southwestern monsoon that brings rainfall for Hyderabad, for example, is that going to confuse my system when it comes to land atmospheric interaction? Urban heat island effects is a land atmospheric process. So, how do you isolate influences of marine or monsoonal effects from understanding what is happening to this land atmospheric interaction? So, you have to isolate, you have to segregate the atmosphere, I mean the region by building a wall of 50 kilometer height on both sides and create a control system, and then assess urban heat island effect. Then you can say you are just talking about whether or not wet surface creating clouds, wet and then creating more moisture, bringing that moisture down. Then you prove that urban heat island effects on evapotranspir or increased precipitation. If that is not possible, I think you can understand why that is not possible, because you have external factors that is going to actually influence these extreme events. Okay? Is that too much? Okay, you can follow this, right? We will have 5 minutes break before we assemble again. I think I am considering, I mean all of these discussions you can read later, but what we want to conclude here is that it is a local scale effect, but it also has regional context associated with it. So, we want to kind of keep that in mind. We will assemble here by 10:37 to start with the flood discussion. Okay. continuation of the previous discussion, I am going to relate this session with hydroclimate temporal variations leading up to rainfall runoff relationships, but later, if time permits, before Professor Venkat Reddy joins us, we will finish some portions of flood discussions, but climate indices, climate variability related indices we can talk about. Yesterday we talked about extreme weather events indices, right? There is a distinction between extreme weather event related indices versus climate indices. So we want to distinguish between those two. We'll touch on those like major ones, ENSO, El Nino, La Nina, PDO, MJO, those kinds of things. It's all on a global scale. But let's start with the temporal scale first. Understanding hydroclimate process is complex due to relatively short existence of humans on the planet, right? Because of humans, we talked about water cycle, how it has changed, and how that is influencing hydroclimatology or hydrometeorology is the one that it's a lifetime's work for us to do justification for answering some of those questions. In the absence of direct observations of climate variables, alternate approach is devised to extract climate record. Basically even people go dating back to few centuries using tree ring records to geologic information to historic information, but then build up to 300, 400, 500 years of record of certain variables, not all of them, but certain variables, and then looking into the future of 100 plus years. So they are able to see at least 5 centuries worth of record on a temporal scale for climate system, not for weather system that I am talking about here. And climate variability, once you have climate system understood, you can really have variations plotted. When I am talking about climate variability, it's a decadal or annual scale variability that we are talking about. I have a graphic to show you to clear that confusion if you have any. And then hydroclimate variability. Okay, those are the 3 things for the climate cycle related topic. What is climate variability and change? We talked about in the first class, but I want to repeat this again. Oscillations are patterns of fluctuations about some specified mean value. Somebody asked the question on what is anomaly, right? We talked about what is anomaly. That is the same thing, variability or the difference from some average number or the mean value of specified period. Yesterday I showed you a graph of deflection from the average of certain variables, right? And that helps us to understand whether or not we have seen the change point or whether or not the trend is still the same. Those kinds of questions that you ask based on the variability. Change is basically the trend consistently going up or going down, that kind of a thing on the longer time scales. The change is viewed as instance of climate variability. So climate variability is time scale dependent on 2 major categories. One is external forcings, changes in forcing traceable to solar irradiance. Like I said all this morning, sun is the main input for energy, and how the changes, big changes, solar storms, or these volcanoes emitting sulfur dioxide or whatever smoke and blocking this radiation coming, cooling the earth's surface. That happened few years ago. One of the big volcanoes in Indonesia erupted and it cooled off the earth to some degrees. So when you plot the long term average, you will see some of these external forcing influenced solar radiance getting impacted. Internal forcings, of course, there are some things, earth is such a complex ball, it has its own dynamics, it changes, how it rotates, how it changes on a day-to-day basis that we are looking at is dependent on some stochastic conditions, right? That is chaos sometimes, that is random, it's not systematic, it happens one time, it doesn't happen another time. So you have to distinguish between you know, both internal forcings and the external forcings to come up with. So, this simple graph, it's not mine, I give the source here, gives you a clear picture about these terminologies. You know, some of you might still see them as hazy or foggy in your head when I am talking about climate variability versus climate change versus climate extremes or weather extremes. Now, in this case we will talk about climate extremes because it's on an annual scale. It's not a shorter time scale event that I am talking about here. Okay, this is 100 years, 500, 600, 700 years. Look at this graph, right, going up and down, going up and down. So, that is the variability from one year to the other year to other year to other year. So, you know, seasonal variability, annual variability, all of those things. The annual variability is not much in this case, it's almost like similar, you know, kind of going up and down, going up and down. So, you are seeing annual variability is there, but you know, more seasonal variability I see, but they are considered as climate variability. What I am talking about is this line, okay, the one that going up and down. Now, within that line you are seeing these dots, high points, right, low point, high point, low point, high point. Those are extremes. One year it's a wetter, you know, year, wettest year, the other year driest year, wetter, maximum value, minimum value, yesterday that you saw in temperature on a shorter time scale. This one is on a longer time scale. So, those are called the climate extremes. So, climate variability is a long term annual variability over a period, and then climate extremes are what is the highest point, what is the lowest point for a given time period, right. Then you identify that as extreme. What is climate change? This red line is a climate change. What is happening there? There is a gradual shift in the mean, or how it is increasing, the trend is increasing. That is, let us say this is temperature, right, yeah. So, I see temperature. So, it is increasing, it can be decreasing, or it can actually decrease and then there is a change point and then it remains flat or it decreases, whatever it can happen. So, in this case it is increasing. So, a nice graphic that illustrates climate variability, climate change and climate extremes. So, you cannot do the same for weather extremes. You can call weather variability from one week to another week to another week. Weather extremes, yesterday that we discussed 20 different indices you can calculate for a given year, but you do not call them as a climate event if it is going to be a multi-year, you do not call them as a weather event if it is a multi-year analysis like this. But in any case, climate change is always over a longer time period. Think about it, climate, anything related to climate is a long. And variability is basically there is a change in a certain way, that is this fluctuations, and then the trend that what we are talking about is the climate change. Okay. So, it is a nice graphic that I wanted to really show. So, it concludes our climate variability, climate change, global circulation related stuff generally speaking. Now, we want to dive into floods. What causes floods? And of course, when I am talking about extreme events, hydrologic events, both floods and droughts, floods probably on a shorter time scale, drought can be a longer time scale that we talked about before. This statistic is based on the US conditions, but I will also show for India. You know, for one decade in the US, there were 8 major floods that caused 1,000 or more fatalities. So, that is the kind of intensity, and then people are talking about the infrastructure damage, more than $1 billion damage, each of them basically. So, you can understand the cost associated with all these extreme events and the human lives that are being lost, caused by both climate variability and climate change. Okay, now we think about both climate variability and climate change, and more dense populations in vulnerable areas, and then of course economic development, SSPs that we talked about, land cover, land use change that is happening. So, all of them are leading to these floods. Think about this on a global scale, it is happening everywhere, it is not confined to one place, right. Severe floods hit all the way in Central Africa, West Africa to India, Mumbai on an annual scale, I mean annual cycle, you are seeing this kind of floating population all the time, right? All the time we are seeing this. So what is the solution? I think during the break some of you asked this question, how do we really design things that will keep these people safe? That needs lot of thinking, right? It needs lot of resources, it needs lot of understanding of science. It starts with data, it starts with collecting information, interpreting or interpolating the information, and then coming up with solutions. Solutions can be of many forms, when it comes to cities like Mumbai. And then think about basins, whether it is Bihar or Brahmaputra. Country of like India size, we are talking about a big loss of both population and also infrastructure, leading up to 2000 crores or so given on any given year. This is the kind of statistic that really bothers a lot of policymakers and people who make decisions to allocate funding for building better infrastructure. But it starts with science, right? That's where I'm coming about. We want to have good models. We want to have good physical understanding of the system. You as scientists want to be able to produce good results for decision makers to kind of use them. How good is the result? That's very important. You cannot just make colorful maps and say this area is going to be dry, this area is going to be wet. It should be science driven, sound science driven outcomes that we want to have. For that, understanding is very important, right? And again, going back to the background here, I'm putting that cycle, monsoon cycle here that we talked yesterday, just to give you the context of what's happening. Many of these floods that happen because of persistent weaker circulation lingering over the cities. Like Chennai, for example, they said it was kind of slowly moving over a week's period. It dumped some 400 inches or whatever the number that they are quoting, high number of rainfall depths that was resulted because of monsoonal rains only mostly, worst in 40 years. I mean, we are repeating, if you see year after year after year, 15, 17, 2020, 21, 24, now every year, right? It's not a 100-year flood, it's not a 500-year flood. Why we call 100-year flood? It's roughly it should be happening once in 100 years. Does not necessarily mean. But now 100-year flood is happening every 5 years. 500-year floods are happening every 10 years. Big events. These are probably 1000-year floods. Who knows? So we are talking about higher producing or higher return period floods over a shorter time periods, heavily impacting people, millions of people. 8 million people were affected in Bangladesh. India and Nepal had over 30 million people impacted. Housing and croplands, agricultural lands were impacted. Big number of deaths, 1200 people died. Mosquitoes and waterborne diseases spread. So you see the spread of the impact. It's not only one dimensional, it's not unidimensional. It really impacts on a large scale over a large area. Okay, so not hurricanes. I think for 2024 report that I discussed yesterday, floods were also a big factor, but I think there were other extreme events depending on the region that we are talking about. But in this case, on a bigger scale, I can guarantee that not hurricanes, tornadoes or cold fronts or heat waves, but floods and droughts are causing more damage, right? That's happening a lot. Extreme events caused by increased atmospheric moisture. Now, when I am talking about a sentence like that, you probably should be able to understand the land atmospheric interaction discussion we had, the feedback cycles that we talked about, positive and negative. So here they are talking about increased atmospheric moisture since 1973. Probably they are using model data, probably they had some field data also, atmospheric data. But in essence, what they are talking about, atmosphere is holding more moisture. And we also talked about that yesterday. Drier atmosphere can hold 6 times more moisture, right? That's what we were talking about in a changing climate. And that 6 times of increased moisture holding capacity of the atmosphere dumps that amount of rainfall quickly over a shorter time period. That leads this discussion to floods basically. Substantial 100-day floods in 29 large river basins happened during this time. Floods and droughts, I am using droughts also in this case, but I think drought needs definitely a different dimension or outlook. We will come back to that later, but I will walk you through some historic context here to give you some context. Egyptian agriculture, Persian water system, Roman aqueducts, these are really age old civilization based management strategies they use for water to protect societies from hydroclimate extreme events. These are innovative ones. And you are right here in Telangana region where tank systems are well known to really have that kind of cushion, when it comes to floods, when it comes to droughts, they use that stored water. They break the flow of water depending on the density of them. The same is true for South India, many regions, whether it is Tamil Nadu or maybe in Karnataka or in Kerala or here. Most of these regions have had some kind of management systems traditionally, but again people modified them, that is a different story. But it is not just local, right? What I am trying to say is global. Extreme events are acute in regions that rely on stream flow for irrigation, urban industrial water supplies, flood protection, hydropower. So these are going to have an effect on multiple things, multiple sectors. Understanding the relationship between meteorology, climatology and hydrologic event is the first step developing the strategy. That is where we were spending our time so far. So if you think about this particular bullet, understanding the relationship between anomalous meteorological, climatological and hydrological events. So we talked about all those three things in the last 2 days of 4 or 5 hours. What is the link? What is the connection? How do we really see when flood happens? It's not just don't look at it, oh heavy rainfall that happens so it becomes flood, just you cannot just keep that narrow focus. Bigger picture, start from a bigger picture. What is the flow of moisture, where it comes from, how it comes from, what causes the connections between climatology, whether El Nino or La Nina in subcontinent, southern hemisphere somewhere that's impacting on a larger scale, and how that is connected to hydrology. So we are now confining it to hydrology in this case, but we talked about climatology, meteorology so far, right? So here we want to talk about floodplains, right? Floodplains are stream channels incised in a relatively flat surface of varying widths. Basically, we are talking about the flow that's happening in an incised channel or canal and surrounded by these floodplain areas, right? Floodplains and river flow or stream flow that happens here surrounded by the flat areas, and then of course you have bank that is really getting elevated. From the engineering perspectives, a weather related flood occurs when the drainage basin experiences unusually intense rainfall. Somebody talked about it before. You get 100 inches or 100 millimeters of rainfall. I mean, we even saw yesterday how we define extreme events for our extreme event analysis of heavy rainfall, extremely heavy rainfall, 3 different categories up to 220 millimeters or so. Exceeding that number is extreme rainfall event, but anywhere when it exceeds 64 millimeters or so we saw as heavy rainfall event, right? So that actually is the first step, and then stream flow is greater than the channel capacity. If this channel cannot accommodate the runoff that we are getting from this precipitation, it's going to spill over to these floodplain areas. Bank floodplain areas are going to be inundated, and the lands adjacent to the channel that is not usually submerged basically are also getting submerged in this heavy rainfall event, right? Understanding the origin of weather related inquiries, consideration of atmospheric and hydrological processes related to a given region is very, very important. What happens in the Ganges basin may not happen in Godavari or Krishna or in southern river basins, but we want to have regional context associated with that. And of course, atmospheric mechanisms play a role In Kerala, I think there is an increased realization that there is some atmospheric river phenomena that's happening nowadays. I don't know, there are some initial queries going on right now to really see atmospheric river process, but we don't have a good source of data to validate those thoughts. Now, when we talk about floodplain and flooded areas, this is an important graph that I wanted to show. The channel that you saw here, right? So, the bank full depth that we have here up to this point, right? And then that is called bank width, right? It's a clear definition, and of course, you have certain amount of vegetation, you have the floodplain or hydrologic floodplain that we have here, and when there is more rainfall, you can see your hydrologic floodplain getting inundated, and the topographic floodplain what we are talking about is one step further. Even with extreme heavy rainfall, if the river is swelling up to this high, your topographic floodplain is also getting impacted. So, it is not just the channel capacity at that point, it is not just the bank full width conditions, and then it also exceeds beyond that point up to the topographic floodplain. So, coming back to global scale analysis, this is from the textbook. I think I may have the scanned chapter for you for reading later on, but just to tell you that it is not one place. You can see Brazil, Russia, China, Bangladesh, US, Vietnam, big rivers. All of these are, Amazon is a big river, Linam or Yangtze, Ganges, Mississippi, Mekong is the one that I have extensively studied in the Southeast Asian region. Vietnam is the most vulnerable spot for that in the downstream side. So, we are talking about flow, peak discharge. You can see the volume of water that's actually transferred during heavy rainfall events, all the way from 400 cubic meters per second. That's a huge volume, right, to 60. Even this itself is the highest number. If you think about this, we are talking about 6 times more. So, huge amounts of water that we are moving during the flood events, right. So, that is happening, but people are trying to really, I am giving you a basic broad view here first before we get into the details. Hydroclimatology wise, I think we are looking at modification to the landscape, right. There are a couple of things people do to protect the flooded areas by building dams, levees, bypass channels, and land use control of floodplains. I mean, that is a very engineered solution, okay, and then barrier islands they put just to make sure that it serves as a barrier. But again, I think understanding floods is really the core part of preparing the place for protecting from floods, right. Flood is closely aligned with hydrometeorology. It is not climatology related. You don't talk about longer time scales, right. Every year when we talk about Mumbai floods, we still talk only the monsoon floods. It starts in June, it ends in August, but when it ends in August, probably it moved out of Mumbai area, but it hits heavily during June and early July, and which we saw even this year. So, it is a seasonal process, so we call it hydrometeorological process, okay, and the combined with atmospheric activity, which is in this case sea surface temperature, that is ideal to have the onset of monsoon that starts in Arabian Sea. June 1st, they normally say. It even advances little bit further. This year I think it started little bit earlier. Climate change might really have an effect on those. So, that is a large scale process, but then again the motion or the movement of these circulations is also influenced, that we talked about just now on the circulation patterns. Broader time and space perspective of local, regional and global atmospheric process is important to understand. I mean, what is happening on a bigger scale? If you are talking about floods in Hyderabad, you want to really think about bigger perspective on what system, what mesoscale activity that brings moisture to the region, and how much of a rainfall that it provides for a given extreme event. Then you plan for it. Circulation patterns for which the floods will actually be initiated is another consideration that you want to have. Flood hydroclimatology, I am still calling it hydroclimatology here because this happens over a long time in the same fashion. isolated and intense convective thunderstorms. There is a connection between hydrometeorology here. So I'm just trying to distinguish in a different color just to highlight that. What I'm saying is convective precipitation means it's happening because of daytime heating. Solar heating that we just now discussed in the first session, 6 a.m. to 6 p.m. is the active period for any solar irradiance to really get split into latent heat and sensible heat flux, and that really provides active atmosphere. It can linger once that atmosphere is activated. The system moves maybe multiple days. It's not just gone for one day. Maybe it's existing beyond one day. If we are talking about mesoscale convective systems, large area systems. And then squall lines. What do we mean by squall lines? These are thunderstorms that are rapidly moving. It's like an arch. I think I may have a graphic on that later, I can show you, but what it means is it will actually start moving very rapidly over a large area, producing heavy thunderstorms, multicellular thunderstorms or storms that happened the day when I was leaving to come here. A big storm that pushed all the storms over the flight path, so they had to cancel my flight for 24 hours. So it has got direct effect on people's lives basically. Extratropical cyclones and major fronts, that's very common in our region, in India for example. Here, these tropical cyclones produce heavy rainfall, whether the anomalous tropical cyclones that we saw last year in Arabian Sea, or this year, that you may see in Bay of Bengal, all the sea surface temperature that becomes really ideal to start these storms, and then these fronts move into the landmass. And this part does not apply to us. Rapid snow melt that happens probably in the Himalayas, but there are many higher altitude rivers that are driven by rapid snow melt that we don't need to talk about in depth here. So for flood protection purposes, we want to have an integrated understanding of the system, right? What causes? So we want to understand the mesoscale activity. We want to understand the source of moisture that's coming to the region, and whether it's seasonal, whether it's annual, whether it's a multi-year event that we are talking about when it comes to repeated, meteorological events, and how we then decide based on that would be helpful on a watershed scale. Now I am coming to watershed scale. Coupling these changes to the antecedent condition. What is antecedent conditions? Pre-existing conditions, right? What we are talking about. For example, if you have enough moisture on the ground, and if you get even a small amount of rainfall, it can trigger runoff right away. If your if your antecedent condition is drier, initial amount of rainfall will be directly used only for infiltration, not for initiating the runoff. And then of course you want to relate that to regional relationship, like I said before, on the anomalous conditions and other controls, along with long-term trends and seasonal availability of moisture. So these are the other conditions related to soil moisture. So now I will talk about the causes of floods, persistence of precipitation due to slow moving nature that I mentioned before, and then small scale and short duration downpours related to mesoscale and storm scale atmospheric process. There are differences. When I say mesoscale, it's actually extending to thousands of kilometers. Storm scales are really localized process. Somebody talked about cloudburst, right? That's a storm scale atmospheric process. Whether it's Bangalore or Hyderabad, when it happens, it is at that scale. Of course, there is some connection to macro scale activity there, and then global circulation also matters. How that is channelized, in the atmosphere, like how that moisture is actually diverted to this particular region, is also driven by some of these jets at the upper level, higher level, 10, 11 kilometers, you always see constantly these jets are moving, and they can actually drive the circulation patterns, and they actually probably goad or drive these patterns, precipitation patterns into a particular region, and it becomes a hot spot for heavy rainfall. that produces floods. That is the idea. And then of course watershed characteristics makes a difference in the way how the watershed is developed. We talked about global scale water cycle, right? How humans have modified and how this partitioning of budget is changing. In the same way, watershed characteristics determine how much moisture is held in the soil, how much is actually released as runoff, right? If the time domain of flooding normally, actually even though the rain must have come and gone, let us say in 4 or 5 hours, a big storm passes through Warangal area, you do not see the response of it in the same time period. It actually comes back with a delay. It may linger 4 more hours after the rain or maybe a day after the rain, depending on the size of the watershed, depending on the condition of the watershed and other aspects associated with that. For urban watersheds, you can say storm cycle is almost identical to hydrologic or hydrograph duration, but in other cases there probably is a delay. The generation of runoff takes time, the generation of peak flow to reach the highest point takes time, but in urban runoff cases the peak runoff quickly comes, and also the dissipation is also very quick, the hydrograph dissipation that I am talking about. So there is that coupling part, the decoupling or the lag that we need to understand. That understanding comes only when you know about the watershed correctly, watershed characteristics correctly, right? And then of course when it comes to flood, there are a couple of things that we talk about, right? People always get mixed up with things. What is the magnitude of the rainfall? What is the intensity? What is the duration? Those are the variables that we need to understand, right? So magnitude first, for example, how much rainfall in volume units or depth units that you want to really have an idea about. When we say 2 inches of rainfall or 50 millimeters of rainfall, 100 millimeters for cloudburst, people are talking about as a threshold. So that is the depth unit, right? The magnitude of rainfall. We are not talking about the duration in that, right? And then the duration, the length of time above the flood stage, that is in the channel that people are talking about, is how much is the amount of water that we see above the flood stage or the crust, and what is that duration when it comes to floods, and frequency, probability of a given flood occurrence during a specified period, commonly taken as 1 year. Basically we talk about floods, 1 year flood, 2 year flood, 5, 25, 50, 100 return periods, right? So those are the return periods that I talk about. There was a question even one time about how can we calculate 100-year floods with 25 years of data or something like that, right? So it all again leads to the same discussion. You have limited data, but how do you calculate 100, 500, 1,000-year floods? Of course, you have statistical method of calculating. How do you do that? You do probability of occurrence calculation by ranking those 30-year records and then come up with probability estimates and then convert that probability into return periods. That is the method that people use in hydrology to come up with return period calculations. I am giving you the definition itself, but if you want the calculation, we can talk about that later. But return periods are used to come up with flood, probabilities. 100-year is another typical example, once in 100 year or 1% probability that we are talking about. Knowledge of these is necessary for engineering design. When you are going to practice as a water resources engineer or a modeler, flood modeler, this is the basic understanding you need to have. What is 100-year flood? What is 500-year flood? How much is required for a given design? For example, the roads that we have outside of this hall, seminar hall, is an interior or arterial road, what we call, right? The highway outside of this campus is a big one. People design systems, drainage systems, for example, depending on the categorization of these roadways. Small roads, big roads, there are more traffic, less traffic, more people impacted, less people, level of service, LOS they call civil engineers. So how do you design them? Based on the number that we give. We want to calculate ultimately what will be the 100-year possibility for this road versus the main road outside of the campus. If you want to invest money, where will you put more money? For this road or for that road? For that road, because it will be connecting more people, more traffic, more importance and all that stuff, right? So higher, they are going to have higher return period calculations for them. Maybe this is a 2-year return period. For that it will be 100-year return periods. I am now using the term return period, so probably you all understand that at this point. What is return period? Probability 1 over t, right? Occurring every once in 2 years. That's the definition for a 2-year return period, roughly, right? So that means you can size the canals, size the drainage structures based on the return periods. Higher the return periods, you need to size those culverts bigger in size, or drainage structures to be higher. So the engineering design that comes into play because of the volume of water that you need to come up with. 100-year floods will have more volume, 2-year floods will have lesser volume, right? The money that you spend for 2-year flood storm sewer systems will be smaller in size compared to a bigger system. Am I repeating what you all know? How many of you know all these things before? Please raise your hand. So it's most of you probably hearing this for the first time, I see. Am I correct? Am I understanding correctly? Okay, then it's not waste of time. Otherwise, I don't want to keep on belaboring this point. Return period, right? We talked about exceedance probability. So the return period is the average length of time between occurrence of a specified flood magnitude. I talked about it. And the exceedance probability is what is the exceedance? 1 over t is the probability. And 1% chance or 0.01 are equal to 100-year floods, right? Basically that's 1% chance of floods. That's a very small percentage chance for a small road like this. For a bigger road, maybe it is important to consider 100-year floods. But again, I think these are the questions that you will ask when you become a project manager to design flood protection measure, flood protection systems in place. Again, the new terminology is flash floods. I think it's a very important terminology in some regions. Are we having flash floods in this region? Does anybody can confirm? Do you know if there are flash floods that are occurring here in this region? No? Okay. So it's important to understand that maybe instead of talking about it, let me take a minute just I think I may have shown this before, have I?
One shopping mall, Ashadam KG sale. KG ki half KG sarees free. Chudidars, men's, kids wear by up to 50% bhari discount. 1+1, 2+1 vanti combo offerlu. Inka marinno offers meekosam. One shopping mall.
I cannot pass this. I have to wait. Yeah, so now. So the dry river bed is seeing suddenly increased flow, right? See, the river was bone dry few minutes before, and rain that happened some few kilometers ahead of this place brought that heavy rainfall with all these dead woods, wood logs quickly coming. See, the dry river bed is suddenly engulfed with water. So this is called flash floods, right? I don't know whether it's happening in this region, but it can happen, right? It's not ruled out totally. It happened in Utah. Somebody had actually recorded this, and they were able to see the power of water, and they were absolutely stunned to see, and they were capturing this from different angles here. It's amazing to watch. So I show this to my class all the time. So I just wanted to show this just to give you an idea about what flash flood means. And sometimes people don't know this. They stand there and then suddenly they get carried away by this water. Forecast is very difficult. It's a 6-minute video. I don't need to waste 6 minutes on this, but I will jump to the last part. Here you can see. I mean, it's massive. It runs through bigger area. I mean, very, very fast moving, and in our case, it may be happening when the land cover change is quite substantial, when there is less time for water to get absorbed, it leads to runoff.
Perfect example of turnaround, don't drown here. Major debris flow.
Yeah, I'll stop there. So that is to give you an idea of how intense the rain can become, or rain can become flash floods, right? And for that, of course, you need to know, I mean, that system actually dumped rainfall far away from this place, and somehow they realized this place will get runoff from that rainfall, so that man was standing and recording that. Again, that alertness is very, very important. So sudden local flooding produced by meteorological scale precipitation, that what I am talking about, over limited space and time produces rapid runoff. That's exactly what we saw now. Mesoscale convective system basically is anywhere from 100 to 1000 kilometer large, number of cells that cross. This is actually in the Midwestern US. You can see how the vast area that is getting impacted here. If you see here, these are thunderstorm cells, convective cells that's moving. This is primarily driven by daytime heating that we talked about in the earlier session. Daytime produces plenty of moisture, and there is no surface or other sources of moisture in this case. Mostly the evaporation leading to convective precipitation late in the afternoon. Many times these MCS happen after 2 or 3, typically at 5 o'clock or 6 o'clock. It happens around this time. So it's all because of this radiation process that we talked before. So again, you need to have a broader understanding of what's the source of the moisture that's coming to the region, right? For flash floods, of course, by quasi-stationary MCS. What do we mean by quasi-stationary? They are kind of moving system, right? Fast moving system, but it's not really stalled also. It's kind of moving, but not at the pace that you would like to see, but partially moving system that can dump quickly heavy rainfall, higher than the weather systems, normally produced rainfall events. And of course, the ingredients for that is deep moisture convection. Occurs during the warm season when high moisture content is possible, and buoyant instability promotes upward vertical motion. I think some of these key points that you need to keep in mind. We touched on those before. I am repeating that again. We saw dry soil, wet soil, how the contradiction happens and how the moisture is moving up upper atmosphere, right? That's what they are talking about. You need heat. In the warm season, sun is producing energy of heat, plenty of heat, and then moisture that's available on the ground is supplying moisture to the atmosphere. And the instability that we talked about, you remember that air parcel and the dry adiabatic lapse rate that we talked about, that air parcel that leaves the surface when it goes up is still warmer than its surroundings. That creates instability. We talked about all that. That creates atmospheric instability, that creates the vertical motion of this moisture, and then that moves horizontally in the upper atmosphere. That's the ingredient. That is the ingredient for the convective systems, right? And then watersheds, where it falls, happens because where actually the rainfall falls and then it produces the flow. physiographic features that are very important, topography, soils and land use. I think somebody asked the question this morning about how do we accommodate changing conditions. Watershed is constantly changing, right? So, we want to consider how watershed characteristics are changing when we design or when we develop methods for estimating flash floods or floods. Flash floods occurs in few minutes to less than 6 hours following a rainfall event, and then suddenly sudden flooding is the expression of intensity and duration, right? We are talking about magnitude to some extent, right? How much volume we want to produce to see the flow, but the intensity matters a lot. What is the intensity? It is the depth over time, right? Inches per hour or millimeter per hour in this case, that is the intensity of rainfall over a short duration. Climate change, we saw in the last 2 days of discussion, produces large intensity rainfall events in a shorter time. That is the deadly ingredient for setting up the system for potential flooding. High intensity, instead of 1 inch that it should be getting, if it gets 3 inches of rain, I should bring it in millimeters, right? So, instead of 25 millimeters, you get 3 times more, 75 millimeters of rainfall in the same 1 hour. The system cannot handle that, right? The system cannot handle. That's what is causing the runoff. Oh, I see the example here. So, rainfall greater than or equal to 25 millimeters for 1 or more hours is called flash flood producing event. It is really a challenge to protect the people and property from these kinds of systems, unless we have understood the bigger picture and also collect data, see how often you get. The example that I showed in Utah, people are very, very familiar. Arizona, Utah, Nevada, these are drier places, and they know when the rain comes, it's going to be flash floods because it dumps lots of rain because of the valley conditions they have. The cloud burst that what we are talking about in Uttarakhand, Jammu Kashmir, Himachal Pradesh region, here it is the same setting that we have there. Flash flood prone areas more prevalent on small streams that drains tens to hundreds of square kilometers, associated with steep mountain streams. That's what I was talking about, canyons and desert washes. Setting, these are the ingredients for that. Orographic enhancement of precipitation with uplift of moisture. We talked about it briefly before. There are a couple of types of rainfall, right? We talk about marine front producing rainfall, convective rainfall, orographic precipitation. These are 3 major ones. What happens with orographic precipitation? We talked about air parcel that's moving up, right? When it moves up, what happens? It cools, right? It cools, but it's still warmer than its surroundings. There is a clash happens over the mountain tops, it dumps lots of rain, right? That's a orographic precipitation. Mountains serve as block. For example, the southwest monsoon that goes all the way from here, west coast of India, that is Kerala, to Maharashtra, to central part of India, to Himalayas, where they get blocked by July end or August. So then heavy rainfall events that we saw in Uttar Pradesh region and other places. That's because of the block that we have from orographic effects. Also combined with the front, monsoon front that's moving north, combination of those two. Ocean front or maritime front that we see in Tamil Nadu, for example, from the Bay of Bengal area produces heavy rainfall events. So the enhancement happens. If the land is already having enough moisture, that we saw from the morning video, small NASA video that I was showing, land is also producing evaporation. But if the ocean front or orographic combination of precipitation that adds to it, it becomes a deadly combination for bringing more precipitation, right? So that's the part. And of course, it happened in many places historically. I'm not going to talk about all the other places now, but let's actually see when it comes to transforming this rainfall. We talk about precipitation a lot, all the time. Okay, that's only half of the story. How that precipitation is transformed into runoff, that's hydrologist's job to really understand how to calculate. So for that, runoff is the metric, basic metric that we use. That is the pulse check for hydrologists to see how the watershed is behaving. if I measure at the outlet of whatever basin that we are in, Warangal, in the Warangal basin, whatever we have, I don't know the name of the river, but I am saying whatever basin that we are in, if you put a gauge and measure the flow at that point, it gives you an idea of what's happening in the watershed. Today, average flow means no rain. Tomorrow, 10 times higher, you must be assuming that something happened in the upper portions of the watershed that drains water, right? When there is low flow, you can assume there is no rain upstream or downstream. So, the pulse check is done with one variable, that is runoff. Of course, when I am mixing up runoff with stream flow, what is the difference between runoff and stream flow? Can somebody tell me? I am giving a break here to catch a breath, but please tell me, what do you think? Can somebody volunteer? You okay, both are correct, but I want to kind of define or refine that statement further by saying that I think everybody heard what they said. What we are talking about, runoff is happening over a flat area. So, when do I stop? Okay, 15 minutes. Yeah. So, we are talking about runoff on a flat area, right? That's not channelized or routed, but when that flow from one cell flat grid, I am talking about horizontal cell to another cell to another cell, and finally it ends up based on the topography into a channel, into a stream, and then it starts like a stream flow. But there is also base flow component associated with stream flow, fed by the groundwater systems constantly. There is some amount of water always there, with or without rain. That is the base flow part, right, in hydrographs. So, we are talking about the runoff that is channelized or routed into a stream becomes stream flow. But in most cases, first we want to understand or quantify runoff in a watershed. That is a basic signature. I call pulse check or basic signature for the hydrologic cycle, for the terrestrial branch of the hydrologic cycle. It's very significant because this amount of water is available for multiple purposes, including keeping up for the demands of the human use, irrigation, hydropower, navigation, environmental regulations, whatnot. So, you need to quantify that amount correctly, and the runoff integration is complex. Of course, integration of complex hydrological processes acting on precipitation after it reaches the surface. See, for yesterday we talked about rainfall as a loss for atmospheric scientists, right, and it's a gain for hydrologists, right. We talked about that yesterday. So, the journey of that drop ends for atmospheric scientists once it leaves the atmosphere, but for hydrologists that journey starts once it falls on the ground. So, it starts its journey once it falls on the ground, it starts flowing. How it flows, where it flows, how do we divert it, it's all dependent on how we define. So, that is a complex hydrological process that I am talking about here. There are a couple of quantifications that we want to make. P minus ET is your runoff, right, that is a component on the left side of the water budget. Some amount of water is stored in the soil, some is stored in the river, some is stored in the lakes, some are stored in the wetlands. You want to quantify all of them if you want to calculate what is the amount of runoff that you get. That is the basic part that you want to understand. Okay, so that is the one. And then watershed scale runoff is affected by a lot of factors, right. So, we want to understand, we know now climate is a big player, physiography, the setting up the watershed, very important, whether it's oblong or normal heart shaped watershed, or what kind of slope that we have, what kind of vegetation we have, those are the things that matters. In the the equation that I showed, the climatic factors P and ET are driven primarily by conditions of climate, right, basically atmosphere drives that, and the right hand side is due to physiographic factors. How much is actually stored in the soil, how much is flowing in the canal, is the physiographic factors, right? It is a control that is given by physiographic factors. So, climatic conditions are on a climate scale, and then physiography is of course happening on a constant time intervals. Quantity of precipitation is very important, and the form of precipitation. When I am saying form, there are many different types of form. I mean, we are generalizing this as one simple term called precipitation. It can form as solid liquid drops, right? Liquid drops of rainfall. It can be snowfall. It can be freezing rain, which we normally get, half melted, half liquid. When it falls on the ground, it is the dirtiest rainfall that you can get, because it sticks on the ground, it slips, you can easily fall. So that is also a source of moisture on the ground anyway, that will melt away. So, and the intensity of that is a form of rainfall that I am talking about, and the intensity of rainfall that we know, inches per hour, millimeters per hour quantity, duration, how long is that rainfall that falls, and then the space and time distribution, how big of an area. We talked about mesoscale convective activity that brings heavy rainfall over a large area versus pockets of precipitation as cloud bursts somewhere happening in a localized area. How often it happens, the frequency of it, that's very important to consider, right? And then direction of the storm movement. Is it moving from west to east like what we are seeing in the monsoon rains, or is that coming from the north to south, or is that coming from east to west in the northeast monsoon from Bay of Bengal? The direction matters to some extent, because then the topography also matters, how the continental southern peninsular India is shaped up, and how one area escapes and how the other area gets hit. We showed you some of the examples of our projects from before, where the Nagavalli Vamsadhara river basin, which is sitting right at the corner of Andhra Pradesh and Odisha region, directly taking all the storms, right? That is impacted by the direction of this motion, of the movement of the cyclonic activities. Again, these climatic expressions of evapotranspiration, again, that is, I mean, basically, I think I'm kind of repeating some of those things here. I don't need them. So this is the water budget part of it, right? So in 100% rainfall, I think we showed little bit on the water balance side, right? We talked about P, we talked about E this morning, and majority of it goes as evaporation or evapotranspiration, right? 70% of your rainfall is lost as evaporation. The remaining 30% is runoff that we are quantifying. So understanding that 70% is very important, but even the remaining 30% that what we want to quantify is based on other factors, like how much is intercepted by vegetation and how much is actually flowing in the river based on the actual moisture content, existing soil moisture conditions, and so on and so forth. So some of you might be seeing, when I say go back to your place after this course and ask yourself what watershed you live in, right? That's very important question that you need to remember. You need to ask anybody in your place who knows it if you don't know, or define yourself based on the DEM, right? I think there is probably, if we are going to run SWOT model, you have to do this as a first step. Some of you might be really familiar, some of you will come to know probably when we introduce SWOT model. So the definition is based on that any drop of water that falls within this watershed will end up at the outlet, right? Anything that falls outside of this ridge line will not end up at the outlet. Simple definition of a watershed, and this condition of the watershed matters a lot for routing the flow. What kind of topography that we have? Is it a flat area? Is it a mountainous area? Forested, agricultural, urbanized, or many different things like that, combination of that. Are there any interceptions, like ponds and lakes and reservoirs that holds the water before it shows up in the watershed? Those are the physiographic factors that plays a role before we define or we want to estimate the runoff or flood producing events, right? So the watershed properties are very, very important. Land cover, land use change, and how much is the water that is infiltrated, and what type of soil we have, permeability, groundwater, lakes and swamps that we have in the watershed. So these are really common factors that you are all familiar with. I am repeating here, but land cover, land use change, go back to that same watershed, right? This is today's condition. This question came up during the coffee break also. today you are seeing the watershed like this, tomorrow all these forests in the upstream portions are gone, okay, assume, and then you have more buildings in other places where agriculture is happening right now. That means you are completely modifying this watershed. Do you think you will have the same flow at the outlet with this changed watershed conditions? Probably not, right? That was the question asked earlier. So, what is the solution for that? You need to consider dynamic land use, land cover change when you are considering long term, especially for water resources planning and management, considering bigger infrastructure projects. Those kinds of dynamic changes are very, very important. But once you are talking about a short scale flood event to manage the flow, it does not matter. Within that particular time frame, change may not be that significant for a given year, given storm. So, that is one thing that you need to be distinguishing yourself from, okay. And then stream channel that we talked about, the incision that happens, the size, shape, roughness and length. HECRAS, when we are doing, probably you will come to know some of those things, like what is the channel roughness factor, Manning's roughness coefficient, that you will probably be familiarizing with, and the shape and size of the the canal network. All of those things matter, but anyway, I think I am going to skip this part because this is the kind of model that we use, right? Any water balance model, water budget model, dividing precipitation into multiple components. These assume that each of these boxes are water budget components, defining with equations. Once you combine all of them in a framework, it becomes a model, right? We are talking about runoff, precipitation leading to runoff, combining all the other factors. In the interest of time, I think I may have to stop here because we are halfway through for talking about the settings of flooding first, but tomorrow I think I will continue from this point for talking about how we will transform this precipitation into flood events, and then I will also talk about climate indices, because sometimes the settings, when we talk about settings, they are also going to play an important role in some regions, if not for all the regions. I will end the discussion about floods tomorrow in the first hour and then continue into the second hour, starting with droughts. That is another extreme event that we want to start talking about, but then wrapping that up on Saturday, because Friday we will have a field tour, right? We are having a field tour on Friday, and then Saturday we will wrap that up and then start thinking about adaptation measures and resilience structures that we want to be thinking about for the remaining time of the semester, for this course. Okay, I will stop here because Professor Venkat Reddy is here. He is going to continue his lecture today for the last hour. We have at least 50 minutes time to go. Thank you. I think we covered a lot of topics here today, so that's why we are going slow. You want the mic? Mic? Okay. Can you all hear? Just hold it.
In the afternoon today, we are going to work on analysis and visualization of flood hazards. So for that, yesterday in the WhatsApp group, we have already messaged you to download the datasets and software that are required. So make sure everyone have the datasets and the software, SNAP and QGIS. Okay, thank you.
Yeah, we will take a quick break and then within 2-3 minutes and then come back so that we will start with the next session. For the hydrologic modeling and how we can convert the rainfall into runoff, we can discuss like a, so when we are modeling, sometimes we are more interested or we need to go for something called forecast. That's more important for us to do to take some measurements for the, you can say, readiness or risk management. to reduce the impact. So for all the things we require the forecast, and so we are basically in this thing we are basically dealing with the like a event based runoff. Means like for example when event is there, especially the any hydrologic event where the rainfall occurs like a thunderstorms. Okay, so suddenly a heavy rainfall like in the cyclonic storm heavy rainfall occurred at one particular region, and it is like a span for few hours or at least only 1 or 2 days maximum or few hours. That like a very means high thunderstorms like only for span for only 1 or 2 hours. So in all those cases, how that can be forecasted early so that that can be known like how much is going to run off at a particular point. So how that can be done and what type of concepts are available right now, what is the modeling concepts available, so how we can really achieve that lead time. So those things one by one we will see. Problem laptop issue. You copy them. You have to copyright. Okay, power is there. way how it is occurring, it is go on predicting the thing with some level of accuracy. So whether we can give rainfall real what is occurring, or we can do this forecast. This is one concept. Okay. So then the second is this rainfall we are giving in the model, right? Then it will go to the, this is all like a model, I am saying like a physics based model, hydraulic model, infiltration, overland and channel, and finally predicting the discharge. Okay. This is the M2. So then it will go to M3, means we can directly see, or we were forecasting, right? We want to make it some correction here. That is like a level M2. So then you can see how the M3 like it will occur actually, the M3. So what is the M3 it will occur? Whatever the data you are giving M2, right? So we can give this one, we can make some inference, so you can say fuzzy inference rules will be there. So accordingly you will correct that whatever runoff you are simulating, right? You will comparing with the previously simulated data set. So we will try to like improve that particular, you can say the whatever the forecast you are doing by already happened event. For example, 10 hours of rainfall you are simulating, right? So first 3 hours already you simulated what is going to occur. Means first what you will do is what is observed you know, and what is already forecasted simulation you know. So you will try to reduce the correction, means you try to reduce the error. Accordingly same correction you will apply for the next 3 hours also. So that whatever the outlet discharge also we are improving. So that's where it will occur. So you can see this how it is really happen. This is the background, you can see data sets, DEM. These are the, you can see the basin. Means like we tried, I said like one is Warangal we tried actually, same thing like we tried, it is like a real time has to occur, right? Later some point at time what happened is some flood occurred and that systems got damaged actually, whatever is installed. We thought like some events already occurred, right? Already some places already this all event based rainfall is already captured, runoff, everything is there. So what we thought is like we can apply for those things also with all the data sets. That's what we tried with a backup data set. So these are the some of those things. We will show you the, these are like for a special event thing is very very important, like how the channel is there. Channel roughness, that is called Manning roughness. I think some of you are with a background of water source you will come to know. That's very important in the event based model. How the channel is there, how that is the way the flow will come actually. So this that observations we need to take how the channel is there, and accordingly we need to apply the coefficients. So some of the, you see how the this apply model will go actually, the cases actually. First one is observed rainfall, then we will go to observed rainfall and simulated runoff. That is case 1 actually, like a, then second case is like this. So observed rainfall we are giving simulated rainfall and then we are updating the runoff, means we are improving the runoff. That is the case 2. So then rainfall is observed, rainfall simulation we are doing, and we are applying here the model actually, the M1 model. So then we are simulating the rainfall also, means like with this we are forecasting the rainfall, then we are applying that forecasted rainfall to this model. We are runoff we are simulating, just we are simulating runoff. Then all the cases, okay. So runoff is forecasted, rainfall is forecasted, then we are doing after you can see this flow is coming, right? We are updating that one. So everything is like a, we are improving, means like it is like a 4th level, like a highest level we can take, like a rainfall we can simulate, forecast, runoff also we can simulate, and then we can improve that one. So you can see this is the thing, it will explain all the things. So I think if you could able to get clear, means this is the way anybody can able to implement this type of forecast models. So you see the thing actually. Now you can see here what is the thing here, actually there is a 4 hour of rainfall is there, right? So with this 4 hour of rainfall is there in the R1, you can see, like a color, you can see the observed rainfall and then forecast and then observed runoff. So you can see here, say M1 model, you are applying the model. So it is like a, so it is like a M1 model, means rainfall forecast is there, right? You see the now 4 hours is there, now we are simulating the another 3 hours of this is what I am saying, the right now event is set, means event is happening. So now is already 4 hours of rainfall is occurred. So you simulated that another 3 hours of rainfall what is going to occur. Okay, then this will go to the forecast model. So you see now only here the 4 hours of rainfall is there, we can able to simulate the discharge, right? Like a hydrograph, that is the last one is the hydrograph. So we can simulate this, what is the runoff is going to occur at the outlet. So this one, you see the 12 hours. So now in this one, first what you have to know here is only 4 hours is the exact one, right? Remaining 3 hours is what? Forecasted rainfall. Means what? With that forecasted rainfall with 3 hours is going to occur, means total of 7 hours. What is the, it is going to be the runoff we got, right? Means event is still not completed, still is occurring. So you forecasted the rainfall and then 12 hours of the discharge is simulated. Means it is going to, what is going to occur at the outlet you are already told. Okay. So like this, you see the, so now this is like just simulated. Means it may not be correct, right? We need to improve that one. So for that, this will happen. Means you see here, what is the difference between this and this one? So here, here this blue color is there, right? This is like a observed, we can say that we are simulating the 4 hours rainfall already occurred, right? Means in the outlet of the that stream, you are getting that by the time 4 hours is already spent, right? So you are going to get what is the observed runoff. So now we have the observed runoff and this is called simulated runoff. Next you can say the 12 hours and these are the next what is going to occur in this thing. Means now to here you see these two things you will take and you will give to fuzzy model. So there it will try to improve this next, you see up to the next like whatever the 7 hours you are simulated, right? This whatever the rainfall. So this next, this one you will try to improve this one, since you have already some 4 hours runoff already available with you. So you combinedly do this error correction and you try to improve these results. You see when compared to this one it is better, right? It is coming close to the what is the observed one. So that way we can able to do the, you can see that is like a fuzzy model, that is a forecasted model, that's improved model. So where only we are correcting the discharge, whatever we did here in this one. Okay. So like this you see here how the things will happen. Then next one more hour, right? It is like this it will happen. 1 more hour, 1 hour, next 1 hour. So with that 1 hour, then it can do 3 more hours extra we are doing. You see, it is a better simulation than the, you see this much you told that it is coming, but this much is only occurred, right? Next 1 hour also this you told like this much is only going to occur. It is better than this one or not? That is what is the like a improvement will occur when your model is happening. So you see, you can say better you are simulating than this one, and then like a further improvement in the, you see, this is like a further simulation. Like each hour, like 1 hour, it is like a lead time is 1 hour. Like each 1 hour the model will go on update the things. So it will tell that okay, next you can say you are 1 hour lead time, this is going to occur, you can tell 1 hour, 2 hour, 3 hour lead time. Okay, same. So like this each and every hour it will continue. So every time the improvement will increase. So you are getting backup lot of observed data, right? Event is occurring, your simulation will become better and better. The forecast, you can say. So this is what is the, you see, like this we can go on improve the things. So just like a complete simulation, just I will show you the how the what at the end how it will be. So you can see at the end is a complete picture like event. So now for example only you don't have any, you didn't do any simulation something, it is the event actually, some event occurred and it is the, you can say the runoff by model, like whatever this one final runoff simulated by model, and this is like a blue color is the observed runoff. Okay. So it is like a rainfall and it is like a runoff without any model. So in between the model means we are all doing this predictions early. That's what is called forecast. Okay. So this is the overall, you can see the concept in the forecast. So this is the involves like a background, you can see the models, data setting and all the things will be there. Okay. I said like we tried for this place, but they said like whenever the event set the start and we are receiving data with all the setup, there is like a flood occurred and it is got almost like a damaged. So you can't able to receive the data from the telemetry and then we can't go on do the things. Then what we did is we did like a backup thing, like already events are occurred will be there, like some places, everything they recorded. So for those things we tried the simulations. So this is something like this. So this is the same like all these models like how like already event occurred means everything is with us, right? Runoff, rainfall is available with us, runoff is available, then we try the forecast and you see how it is really doing for the data which is on the already occurred events. That's what we tried actually here. So this one all of those things, this is what I am saying important one, lead 1, lead 2, these are 3 things, leading times. Means what is the main observation you see, you tell me here, what is your main observation? So lead 3 hour lead means like for example now 3 hours later what is going to take, I am saying 2 hours and 1 hour. So 1 hour time lead is right, there is a more correlation, like it is better prediction. If you are go on moving away from the more time you are giving means it is reducing the accuracy. That's what is the main observation here. So most of the models will be like that. So since we are already some backup data will be there, we can go on improve. So this is where we can make in the forecast. Very very important in these forecast models. And one more thing is we are going using all those 3 models, rainfall forecasting and then runoff improvement. Then the accuracy will be more when compared to simply the only rainfall you are using and then forecasting we are doing. So you will use the all these things, rainfall forecast, model simulation, then forecast means improving the runoff also, then we will get the better thing. Okay. So this is like you see the when compared all these cases, you see this case is the better, means 4th type of model. That's what is the thing observation. So we tried the, you see the 4 like different simulations we are using with the case 1, case 2, and these are all the like different things. What is the main observation you have to get, like all those things, dotted lines like where you are going to simulate and the blue line is the already happened. So within the lead time you can get all these things. That's what is the thing. What is the way I showed all the things we can see in that way. So in all these things, what is the main observed point actually what I want to tell you. So fuzzy logic, but how slowly it is converting into machine learning algorithms. Now fuzzy logic means that is all like a same type of mechanism we can provide in the machine learning. Somebody asking like a prediction we can do or not, we can do same type of things. So in the fuzzy logic is like a, we will also, there also will give it some training. So there will like it will make a some fuzzy inference. With the data set it will give a different alternatives. So then we can take all those alternatives, we will make it into one defined output and then we will make in the fuzzy model. Okay. But in the same thing we will do in machine learning also. We will train the with the different type of algorithms and we can see which one is the close to the some observed data set, that we can take as a simulation and we will do that one. But anyway soon within next we can say couple of days we are going, we will come to know more about those things. Okay. So that like we can able to make that lead time runoff, we can how much you can able to do that improvement, that is all like we can do that one. And this is the overall you can see the we can improve the once after getting the runoff model we can do that updating algorithm, that's really improve the forecast. Okay. So here same thing we told like we are trying with like some event on these things. So then what we thought like say it is like a very small basins we tried, like these are like going for a bigger basin. So just that thing I will tell you what is the way we did. This is the like exactly the spark like as like a Sridhar and myself and then we with one more professor from Texas A&M University. So this all like this is what we made as a real time forecasting model for the floods. So in that the SWAT model is one of the input. So we tried this one for the a bigger basin. Same thing like we are explaining like Nagavali Vamshadhara basin, right? We tried for this one. So just I will show you quickly so that we can catch the time. So this is the like as we said like we are previous Sridhar and we both like with other all the students, and then we made a very you can say that almost like 4 years we worked on this one particular concept. So it's like a rainfall and temperature. Now we said like we are doing modeling, right? It will take time actually. So we thought like we can take some forecast already available from the GFS data that we can improve. That is the thing. This thing means we are improving the already somebody's forecast. Instead of why we are doing, we do for small area, right? They will do for a big models actually, climate models they will do forecast better. So this is what exactly the thing. So this is the way we can do the things, it will make better. So here we will do the forecast rainfall. That forecast rainfall we are giving for the SWAT model. So normally SWAT model is a continuous model, right? Already we built that one. So then we will apply for a one event. Then we can give the input that as a only for a particular event. So it normally work for longer duration, but one event data only will verify how it is occurring actually, how is happening. So here then whatever the in the SWAT model, right, we will only get SWAT model like a outlet, what is the discharge, like a hydrograph. On different parts of the, you can see that particular basin is there, we will get hydrographs, right. So that we will give input to this across. So that across will give you the, that what is the, what we can call as the flood. So you are getting at this forecast, how it will work. So forecast rainfall you will take from somebody, you will do bias correction, input to the SWAT model or any model, like we are, tomorrow we are going to see like a HMS. Same thing we can do HMS also, or any WIC model, anything is okay. So then that inputs we give to the, only that any of those models they will give the hydrograph at different locations. Those things we give input to the across, that will give the spread of the, like a flood. Each hour, each time step, what is the flood going to occur, it will tell. Okay. So most of the flood simulation now is happening with this concept actually. You can see either NRSC you are going to see, right, NRSC or other places, all the, some of these things they are following these concepts actually. So this is the, finally we made a like a one, we can say WebGIS model where we can see this one. This is also we tried, it is up to some level. So we brought on, then further work is happening on these concepts actually to improve further, to make it as a real time. So here so this is the overall concept. These are all things already showed. This is the like a, to get all the basic data sets of those things. So all the team they are like a, this is like a first like a one cyclonic event is there, right. That what we did is like a cyclonic event also, what we thought like a better maybe go for a WRF model, weather resource forecast model. So one cyclonic event is going to set, right, we give the boundary conditions, we can simulate also. You see in this case the rainfall it is we can able to make actually, so simulate actually. So this is like a one, we are, you see like this is like a spreading when it come into land, right. So there we will come to know what is the, it is set somewhere in the ocean, right. It is, time will take, right, it is coming to landfall. So by that time we will come to know how much rainfall is going to occur on the land. That is the input first of all, that's what is the thing this WRF model will do. So in the WRF model any event it is set means with the boundary conditions we can able to simulate the, what is the, you see this is set, by the time it is coming here we can forecast. That we can give as the input to the next, you can say the SWAT model. So now after that thing, whatever is the, you can say the model, so we will give to the SWAT model with all those inputs, field observations, everything. Then it can simulate. It's like a, we are doing for normally for a long term, but we will apply in that wherever there is event occurred. Once model is set, right, calibrate, validate means later it will work. Any event you can give input, it automatically will simulate. That's what is the concept here followed. So here once after doing that one, that input is taken and then applied on this. You see from here to here, this is the main, you can say the reverse stretch. It's a two-dimensional flow actually. Two-dimensional model it is set that this across model which you are going to see. One-dimensional maximum we are planning to explain you. You can see how this is set and then how you can apply. So different points, like you see this is a one junction. These are the different locations, right. All those places we can give the hydrograph as input. So that hydrograph we can once after simulation with this across, right, you will come to know how the flood spread is there, like a, you see this is like every time step how the flood is going to spread on that, we can see the area. So like every time step we can see what is the way the flood going to distribute actually. So this thing like a, we our main goal actually the, our plan is like this, making as a WebGIS model. Like WebGIS means like anybody can see, like for example we keep in our website, website, it is going to occur, event is going to occur, everything we can do an automation. We could able to see that forecast how that our runoff is going to, flood is going to come in a area. But we didn't reach the stage, but it is a different means at the level of, we made as a backup model, we prepared this thing. So it is up to some level of accuracy, it is working currently. So but we are need to further, we need to work on this one. Yeah, that's what is the main thing actually here about this one. So now this is very one of the best times you can see for the forecast systems. So a lot of things are happening in this area actually. So like where previously we use fuzzy or other things, right, this AI and these things will make it better. Since like a lot of variations are possible, we can make the lot of, we can say the training well in advance for so many events, right. So it will take those things, okay. and lot of things is happening in this area, like a speed in the, you can say this, what we can call a computational speed. In future, really somebody interested in forecasting, right? That is one of the area where you can try. Lot of things are changing, like speed. So now what is the current like a level of computation is happening? The simulations or simulation aspects. So now current simulation is maybe sometimes they may there, later they are going for the more you can say changed version of the simulations is happening at quantum computing. But it may not happen immediately, but this area like where especially weather forecasting and hydrological, especially the flood, all those things forecasting, they are going for a quantum computing where this all will occur in a more speeder way, okay, on parallel computing. So if you are available a higher speed like a computing at a parallel level, you have to make early, right, 1 or 2 hours early you have to simulate, right, that is possible with these things actually, okay. So then these are all like a connected things, you need to have this type of systems, you need to have this type of systems, and then these things, then you can make your forecast better. Most of the, like we are visiting place, right, NRSC and INCOIS we are visiting, right, those in the, you can say there. So you can see some of these things, systems they are developing, you can appreciate and you can see those things. On a Sunday we are planning to like a where like a networks like a in the this like a I connected, these are all connected things, not like a alone independent. Like we need to measure something at accurately at gauge stations. That has to be telemetry, we need to send to the places to the, I can say all the, I can say database. So this they are doing at the gauge stations also. So we will visit some of those gauge stations, how they are doing really. So those things we will check actually. Okay. So that's all, like this is about thing. Yeah. So the further like here now lot of sensing techniques, right? No need to depend on somebody's actually. We can make our own open hardware. That is like a current one of the, we are using one more, you can say, project we are working on those things. How to make the sensing instrument to measure some of the process. Okay, that's a different thing. So anyway, this is all things. Now it is like a open. 2 minutes we will conclude the things. We are done with the class. So why it is important actually, this forecasting actually so much, anybody, any modelers especially for this domain, they are very much interested in this thing. Why we are so much interested in forecast? Early warning system to develop and finding the impact, reducing the risk, all the things is very, very important actually. So event based forecast, which are the models. So current actually I said like a HMS you are discussing, and HECROS for the flood, weak models, those things are like a very well, you can say especially events, which are very like a small events are occurring, you can go with that models. So like a current technologies, right, is like a simulation, sensing net, those things, so they're all like important in those things. Yeah. So like whatever I said, like we are discussed actually, there's like a one like our group actually with scholars like myself, Sridhar, and then these are all like a other professor from Texas A&M. They're all like a, everything is available in public domain now. All are available. So some of you are really interested, you can take up some of these things and you can read whatever I presented. Everything is available in the now public domain actually. So that's all for this thing. So any other things, questions, or otherwise we'll stop at this point. Yeah. Yeah, that is the exactly where the one is like a one previous concept is a fuzzy inference system, right? So we will try to see the previous one, right? Previous things. There is observed and simulated already. We are some old events are there. So already we know like whatever we are simulating and what is the error we are going to get. So those things we will take the error. That error reduction algorithm is there. Means like we try to make that reducing the, means we try to bring the whatever the simulation toward the observed one. So there you will get some coefficient, right? Like that first one is like how the simulation fuzzy inference will take place. Both are input and output is known. Then you tune for the coefficients, right? That coefficient you will apply for the next, we can say in the next time you are applying, you will apply the coefficient for the simulation. There we will get the runoff. Transfer functional, that is called actually fuzzy inference system. There is a, all those algorithms available in the, we kept in the papers actually, there is some algorithms are there where we can get that that fuzzy inference, there we can call as the fuzzy inference functions or fuzzy inference system. So every rule like this is the error, this is the way it will come the thing. Like we will make some rules. Accordingly, each rule, like we will try to make some weightage. Like a 3-4 weightages will come, right? Like this is the particular simulation, this is the error, this is the coefficient. So like that we will make some rules, right? So later when simulation comes, what it will make? Same rule it will apply. So everything it will come some coefficient, right? It is weightages. That is called actually the fuzzy. It is not a definite. So then once again what you will do is you will convert into defuzzification. We will convert that into exact value based on the weightages. Then we will get a one value that we will present to the forecast. Okay. So more details like really interest means you can see those things actually all those things are available in the paper. So you can see really lot of all the background equations, those things, everything is presented. You can really somebody interested means you can see, and any discussion on those things also, since all those things we both are involved, most of the things actually you can get to any aspects of forecast, those things we can explain to you more majorly. Is that okay? We will stop here, then we will proceed for the lunch and we can join to the afternoon session. So you may take extra like a 5 minutes, like we may start at around 2:30 we will start, then 2:30 we will start, so that we will take some breaks since okay, right, 2:30 this thing, yeah, 2:30 we will join for the next session. So by that time everything will arrange, but if you want to make any announcement.
Madam, mic on.
Hello, good afternoon everyone. So today in this session, we are going to work on analysis and visualization of flood hazards. Okay, so think like if you want to analyze flood hazard extent, like how much an area is being flooded, you need data set to analyze the flood hazard extent. So the data sets also like before the occurrence of flood, how the area is like, and after the area got flooded, how the area got changed. Okay, if you have pre-data and also post-data, then you can analyze how the area has been changed due to the floods, right? So we need to consider pre-flood data and also post-flood data. Okay, so that data we are considering as satellite images. So satellite images, we have a number of types like Landsat images, Sentinel data, MODIS and all like that. So among the available satellite images, we need to select the satellite image that is best suitable for our analysis purpose. So as we are working with flood analysis, we will take Sentinel-1 satellite images. Okay, why? Because Sentinel-1 uses radar pulses. So it emits radar signals, and when they hit the target or ground object, they'll reflect back. So during the rainy season or precipitation, when the precipitation is occurring, the atmosphere will be covered with clouds. So whatever the light, it should penetrate through the clouds. So Sentinel allows the radar data to penetrate to the clouds. For this purpose, we will consider Sentinel-1 satellite images. And also Sentinel-1 data is an active sensor, like it can operate throughout day and night. So we get complete coverage of the area throughout 24 hours. So we are considering Sentinel-1 images. And now I will explain in brief what is the process that we are going to do to analyze these flood hazards. After that we will work on it. Okay. So after selecting the satellite images, we cannot directly analyze them to visualize the floods. So before analysis, we need to perform some pre-processing of the satellite images. So pre-processing means the satellite images may have some distortions or noise within them. So we need to remove all the distortions before using them for the analysis purpose. Okay, so this pre-processing, removing all the noise or any distortions and applying their exact geographical locations, all this processing will be considered as pre-processing of satellite images. Okay, this step we will do using a software called SNAP, Sentinel Application Platform. Okay, so after the pre-processing from SNAP, we will get the exact data that is required for analysis purpose. So that data we will analyze using QGIS. QGIS is Quantum Geographic Information System. Okay, so using that software, we will analyze how much area got flooded, how the impact is. Everything we can analyze using that QGIS software. So this is the overall process that we are going to do in this session. Okay, so first of all, I hope that everyone have downloaded the data sets. I'll show you how to download them now. As it takes time, we told you to download them earlier. Okay. So as I told you, we are working with Sentinel-1 images. Okay, they will be provided by European Space Agency ESA, Copernicus. So you just type ESA Copernicus in the search bar. Here you have explore data. So once you directed to this page, you can log in. For first time users, you need to register. So click on the Sentinel Hub. Here you can register. It is a simple step, like after giving all your details and email ID, an activation link will be sent to your email. Upon clicking that link, you will be directed to the a dashboard, like where you can access the data. Okay, fill in all the fields and accept the terms and conditions, and then click on register. It's just a simple step. You will get an activation link to the email. Would you like to do it now, or shall I show how to download? Are you trying to register now? Yes, try. Please try to register and check your email. Click on the activation link. If anyone is facing problem, please let me know. Okay, shall I proceed to login? You're not going to download any dataset now because it takes too much of time. You have already downloaded the datasets, right? So just I will show you how to download. So once you log in, this is how the page looks, and you can go to browse the datasets. page looks like, where you can browse the data sets. So if you zoom out, you can see the patches where this Sentinel-1 data is available. Sentinel data is available, okay. So go to search and type the name of the place or study area that you are focused to analyze. So for this tutorial, we are going to work with a flood that was occurred in Ernakulam, Kerala during August 2018. So I am selecting that location. Okay, so here is the place. So we need to search the available data set tiles that were covering this area. So for your reference, you can place this location mark here. So this is the area of our interest. Okay, now we need to find data sets of particular date range. So I am saying that the flood has occurred during August 2018. So we need two data sets, one with the before the occurrence of flood and one data set just after it got flooded. Okay, actually from June 2018 onwards, there is heavy precipitation in that region. So we are going to consider pre-flood data during the end of May. And the peak flood has occurred in second and third week of August. So the last week of August can be taken as post-flood satellite image. So we are selecting Sentinel level 1 ground. So here there are various options, like the first one is raw data which is unprocessed, and this is a complex data format. This is ground range deduction. So we are going to select level 1 GRD. So here is the time range. So I have given these date ranges. Now let us find the available tiles. See, if you place cursor on a tile, it represents at what time stamp it is available. See here, this one is May 29th. So this is June 10th. So like that, you need to select the particular date which is before all the precipitation has occurred. So this August 21st, 2018 can be considered as post-flood satellite image. So you can directly click on the download link that is available. So before that, check whether the tile lies in your study area or not. So here the green colored one is the tile. So you can directly click on the download link. So it starts downloading. It takes a longer time to download. So I am not downloading it now. Okay. Everyone clear till now? similar way, you need to download the satellite image before it got flooded. Okay. So now let us move to the data sets that we have. So this is a folder that we have shared in the Google Drive. So if you observe, these two are the data sets. Okay, you can clearly see the timestamp here, 2018 May 17th, and the next one is 2018 August 21. Okay, so this is before all the precipitation has started, and the next one is post flood. So we got the satellite images. So the next step is to pre-process these satellite images. So we are pre-processing them using Snap. So open this Snap software. Okay. File, open product. So go to the location where you have downloaded. You can directly give the file without extracting. First, let us work with the first one, like 17th of May. Open that file, you can see it here. Is everyone able to open the file in Snap? Okay. Now shall we proceed?
Make sure that everything is different.
Okay, so once you have added the data here in Snap, if you see here the bands, you can see the 4 available bands. So here the VV, VH all corresponds to the polarization. So polarization is like how the electric field is, whether it is vertical or in horizontal direction during the incident and also during the reflection of the wave. So depending upon that, we will get the bands. So VV means here when the radio waves are passing through the atmosphere, the electric field is in vertical direction when it is passing towards the ground, and while reflecting the second path, V means it is also in vertical direction. If it is VH, while reflecting back, the electric field has changed direction to horizontal direction it is. So generally for analyzing purpose, we consider VV polarization scheme. Okay, so we take always VV, vertical and vertical. It depends on the alignment of the electric waves. So if you double click on that, you can visualize the Sentinel-1 image that we have downloaded. Okay, this is how the image looks like before pre-processing. Now we need to apply pre-processing techniques. So what are they means? The first thing is we need to apply orbiter file. Okay, before doing the pre-processing techniques, I'll just explain what are the pre-processing techniques and why we are applying them. The first one is applying the orbit file. Why this orbit file is needed means, so when the sensor acquires that image, it will take approximate locations of the ground. So the location, whether it is x, y, z, or the velocity of the satellite or the timestamp, they are not exactly representing that particular location. They are approximated to some 10 meters. So, in order for analysis purpose, we need the exact orbit data. So, that orbit data will be stored in a file that is available in Snap. Snap will direct that from ESJ, the website that we have seen earlier. So when we give here the image, based upon the timestamp, it will take the associated orbit file from the ESJ website, and according to that, it will process the orbit data for this sentinel image. So we are going to do orbit file correction. Okay, that is the first pre-processing step. And after that, if there are any noise present in the satellite images, like thermal noise, we need to remove that. So the noise generally occurs along the borders, all the borders of the image. Like sometimes we see some vertical lines brighter in color like that. So those are noises which are to be eliminated for analysis purpose. Okay, so we need to apply corrections for that. And also sometimes due to while radar is passing reflected signal, when it is passing to the sensor and it is capturing, along with that signal, some disturbances that were created in the sensor instrumentation, they will also be captured along with the signal and presented in the data. So that noise should also be avoided. Okay, so that data will be provided by ESJ through some metadata files that Snap will take directly from ESJ. So when we apply that noise reduction, that all noise will be removed. Okay, is it clear? And then next pre-processing technique is calibration. So calibration, why we need to do calibration means, generally the Sentinel-1 image data, that will all the information will be stored in digital numbers. Okay, so for flood hazard analysis, we are analyzing two data sets, pre-flood and post-flood. So we perform raster calculations in the next processes. So with using digital numbers, we cannot do that processings. We cannot calculate that raster difference and all. So for that purpose, we will convert that raw data into backscatter values. Okay, so calibration is performed based on calibration coefficients that will be provided, that are available in the metadata files. So when we apply calibration, they will take that calibration coefficients and they will convert the raw data to backscatter coefficients that will be useful for analysis purpose. So we are converting the data sets. Okay, so that is calibration purpose. And the next one is, we will perform speckle filter. So speckle means, in an image, something like grain size, if you zoom into the image, if we observe some grain size dots in the image, which are due to, like for suppose, if the radar is target on a particular building or something, so if there are any trees or any objects near to that, when the signal falls on that particular aimed object, it will also fall on the nearby objects. And when the signals reflect back, all these signals will also reflect back from the plants or any vegetation or any other target that is available. They also reflect back from that. So when they all reflect back and go, so they will create some disturbance to the aimed object. So that's why we observe some grain sized disturbances in the image. To remove that disturbance is called speckle, and to remove that we apply speckle filter. Okay, So these are the pre-processing techniques that we apply in this software, Snap. After applying all this pre-processing, we will get the image that is best suited to perform the analysis. So now, all these 4 pre-processing techniques, 4 or 5, instead of doing each one, we can group them like a tool. We can build a model so that if we give the input data, all these pre-processing techniques, whatever we define, will be performed automatically and the output will be stored where we give the location. Okay. So for that, if you go to tools, you will find graph builder. So you yourself creating like a model you are creating. What all the steps you need to perform, you are creating on your own. Okay. So here you already have read and write. Read is nothing but what data to read or what data to take as input. Write is something like output data. So in between input and output, you need to process all the pre-processing techniques. Okay. First of all, right click, delete this write. Okay. So we have this read file, which is nothing but the input that we have added. Now, to add the pre-processing technique, right click on this. Just simply right click on it and click on add. Okay. Radar. So first we discussed about orbit file. Okay. Simply right click on this window, add radar, apply orbit file. Okay. Is everyone following? So after that, similarly, add thermal noise removal, which will be in radiometric. So add radar, radiometric, thermal noise removal. Yes. Now I'll add all the pre-processing techniques here and I'll stop for everyone to complete. So radar radiometric calibration. Next again radar the radiometric calibration. Speckle filter. In the radar, at the bottom you will find speckle filter. And also one more pre-processing technique, that is terrain correction. So why we need to apply this terrain correction is, terrain is nothing but the elevation of the ground, right? So when the sensor passes to capture the image, the Sentinel-1 will have side-looking sensors. So it will pass the signal at some angle. Okay. So when it aims at some hills or mountain regions, the height, it may not capture exactly the terrain elevation data. So for that, if we give terrain correction and if we give externally the DEM of that location, DEM is nothing but digital elevation model. So for that particular area, if we provide the elevation data set externally, that is available in Snap, if we provide the DEM data, so it will auto correct if any distortions are there in the elevation values. Okay. So for that we will give geometric terrain correction. So these are the 5 pre-processing techniques. So after performing this pre-processing, we need to write the output file somewhere. So input output, write. So this is the whole process, starting from the data input data set to output. See, after this we need to connect it, like starting from input data, what is the next step? So we need to connect everything using arrows. So if you right click, just connect graph will be there. If they are arranged properly, you can directly click connect graph. So everything will be connected automatically, or otherwise you can manually connect it. See, if you place your cursor here, red mark is appearing, right? So if you click on it, and you can drag to whatever post-processing technique that you need to perform. Okay. Right click, connect graph. So it will connect in order. whatever we've added in the window here, you can see them here. So you can change the parameters in this section. Okay. So first, coming from read. So read is where you will give the input data. So as we have already added the data in Snap, so it will directly take that input data. Okay. So we are applying orbit file, auto download. It will be downloaded automatically. And then coming to thermal noise removal, as I said earlier, we'll mainly work with VV polarization. Okay, so we need to select VV here. So we'll take this VV band over here and work on removing all the noise or performing all the pre-processing techniques. And then calibration. By default, it will be auto sigma band because we are converting digital number to backscatter values. Backscatter values are represented with sigma naught. So that is why it will be automatically selected. Speckle filter. We'll be having different filters. Mostly Lee sigma and refined Lee will be used for flood mapping purpose. Coming to terrain coefficient, as I said earlier, you need to select the digital elevation model for terrain corrections. Okay, if you observe here, you have various options which can to select. Okay, here SRTM done. We select 1 second and 3 second, two options are there. So 1 second means the resolution it varies, 30 meter resolution. If we select 3 second, it comes to 90 meter resolution. So we'll select 1 second resolution, which will be automatically downloaded. And then here we'll reproject the image. So if we click on this map projection, another window opens which says map projection. So we'll convert it into QTM projection. So here WGS 84 means it considers the earth curvature into account. So geodetic system. Okay. So when we convert it into UTM system, it takes the earth curvature into a flat surface, which is good for analysis purpose. So that is why we will reproject it here. So if we click on it here, depending upon the location, see it will come zone 43. So the region specific. These are like local datums. So we are converting the projection system from WGS 84 to UTM. Next is to write. Write means to save the file, that is so here you have to select, choose the directory where you are saving the files. Okay. If you want, you can change the directory and you can save wherever you need and click on run. It will take some time. Okay. So meanwhile, you can save the graph that was built for further analysis. Like you need to repeat the same process for post-flood satellite image also. Okay. So all this process we have done for one satellite image before flood event, right? So the similar way you need to take the second image and process this pre-processing techniques. Okay, so you can save this graph for later use. File, save graph. Okay, you can save any location. So for those who have generated the output file for this, you proceed with the post-flood satellite image. Okay. Once you save this graph, when you are doing it for second image, you can load that graph. Load graph, go to the location where you have saved, so that it will directly appear there. Okay. Open. Then it will come here. Give the input file. In the similar way, give all those like dem and map projections, polarization, everything you need to assign and save the output to a location. That is for post-flood satellite image. Okay, those who have completed this, just proceed with the post-flood satellite image. So excuse me. Take a break for 5 minutes. Meanwhile, the process will complete. Okay. Snacks are available outside. Okay. You need to do for post-flood satellite image also. Okay. If anyone didn't complete for the post flood, let it be in a part. Okay, it will compute. So take that processed pre-flood satellite image. Okay. So if you click here and extend to bands, okay, you will see sigma naught VV. Sigma naught means because we have changed the calibration from digital numbers to backscatter values, it appears to be sigma naught. As we are working with VV polarization that we have chosen during pre-processing, right? In the thermal noise correction, we have selected VV only, not VH. So that is why it appears sigma naught VV. So that band is coming in the output file. So now here this image contains linear values, linear backscatter values whose range is too large. Okay, so now to minimize the range of values, we'll convert them. So if you just right click them, linear to or from decibels. Okay, to minimize the range, we are converting this. Yes, convert. So this is the converted band. Okay, this is just to ease the analysis process. Okay, just right click on the sigma VV, then convert to dB, linear to decibels. Okay. So generally the backscatter values range from -30 to +5. Okay, what does this backscatter represents means? If a radar signal hits a hard surface, then it reflects back with much intensity, right? With greater intensity. So it will have higher backscatter value. So from -35 to +5 is the range. Then the higher value would be like 0, -1 or +5 till +5. It is the higher range. So if the signal hits the water surface or any smooth surface, it will reflect with much lesser intensity. So it will give lesser backscatter value, which will be around -30, -20 like that. Okay. So here we have converted the range. So in this image, if we have any null data set like null region, the region with no radar signal, okay, it will take some arbitrary value by default. Okay, that arbitrary value will create errors while processing them in the QGIS software. So to avoid that errors in the analysis part, if any null values are there, we are assigning a value like -35, which is out of the range. -35 like that, we will assign that value to the null points. Okay, that we will do in next step. So after pre-processing, we are converting the range of the satellite values. Okay, after converting the range to decibels, we are assigning some fixed number like minus 35 to the null points. So for that, go to raster band map. So whatever we are performing it, the output should be saved. So here we are giving a name to the output file. So my file, that one is output, like post flood satellite image. So I am giving post flood underscore VV. So with, if you are doing it with pre flood image, give the name accordingly. And replace nav values or infinity results by minus 35. Okay, and then we need to give an expression. It's not like only minus 35. You can give any value that is out of the range, because it should not interfere with the particular range of minus 30 to plus 5. Okay, so to avoid the confusion, we are giving out of range value to be like minus 35. Okay. So if you see the expression, if sigma value minus 100, so if it is within that range, then the same value will be retained in the image. If not, else we will assign a value 30 minus 35. Okay. So if the value is up to minus 100, we are keeping it the same value as it is. If it is beyond that, we are considering them as null values or no signal return values, and we are assigning value minus 35. Okay, so that expression means that. Click on OK. So the post flood VV will be generated. So this is what we need for analysis purpose. Any confusion for anyone? So do it for the another satellite image also. So this is my pre-flood event sigma VV band. So first we are converting the values. So sigma VV underscore VB will come. For this you need to apply the expression. For that you need to go to raster band map and then give a name. That is the expression. Okay, shall we proceed further? After changing this calculation part, you need to save the product. Okay. So first select this pre-flood event, go to file and save product as. Okay, here go to file, save product as and save it in a location. to the post-flood product also. Selected product, go to file, save product as. Okay, so now these two post-flood as for VV and pre-flood as for VV, these two are the final pre-processed images. So these two we need to take it into QGIS for analysis purpose. Okay, with this step the pre-processing was completed. So these are the saved products. Okay, if you open that, so this product you need to open in QGIS. Okay, .img file. So after saving the products, now open QGIS.
Thank you.
Okay, one small suggestion to everyone. So when you are running with these files and images, everything should be located in a single location. If you change the locations and all, at the end they are not uploading in futures. We are facing problem with uploading them. Okay. Yeah.
Might be there is a mistake where we have done this correction span map. Somewhere